Heartfelt thanks to our quality for teaching God's blessings for us.
Welcoming means all unknown guests, Tony and his friends. Then say, to welcome all the outstanding luminaries,
The dignitaries,
the eminent professors,
the passionate participants,
and the studious students. We humbly request Dr. H. Anandar, Assistant Professor of the Department of Physics, to welcome the convention.
Sir, please.
Respected dignitaries, respected chief guest of the second day of International Conference on Material Science, Professor Dr. Sorati Kiwo, Chula University, Bank of Thailand, respected head of the department, my dear colleagues and participants from other colleges, and my dear students of the Department of Physics. Good morning, all of you. First, let me welcome Dr. Sotin K.R., Professor from Chula University, Thailand. I will also introduce him to you. Professor from Faculty of Engineering, he is heading the Department of Chemical Engineering in Chula University, Bangkok, Thailand. He is leading the research cluster on energy storage. He received his doctoral degree from the University of Tokyo in 2004. In 2004, after his PhD, he has joined as the Faculty of Engineering in Chula University, Bangkok, Thailand. His main research focuses on sustainable energy storage technologies, that is zinc air batteries, zinc ion batteries, and zinc iodine batteries. He has published more than 180 research publications in high impact factor journals. He is also an editor of international journals. At present, he is guiding 7 postdoctoral fellows, 6 PhD students, and master students. He has visited several countries for research like Japan, Singapore, Germany, South Korea, France, Denmark, etc. Also, he had given many invited talks in the national and international conferences. When I saw his curriculum in his portal, it was amazing that he has completed several projects and also is doing several projects mainly application oriented. So with this experience, such a vast experience, professor is an expert. He is going to deliver the keynote address today for the second day of this international conference on material science. So welcome you, sir, for this second day second day of the international conference. So before going to his session, let me just present a recap of the first day of the conference so that Professor will also know. The first day, yesterday, our international conference on material science started with the presidential address by our beloved principal and a special address by Reverend Father John Prakasan, our rector, and inaugural address by Dr. J. Kumar, Vice Chancellor of Madurai Kamaraj University. The felicitation was given by Reverend Father Secretary Dr. Dept Camillus, and in the technical session, before that, Reverend Dr. Francis Xavier, Rector Laila College, also gave keynote address. So in the technical session, Dr. Sumit Kumar Avasti gave an invited talk on biosensing applications of botanic crystals. And during the paper presentation, there were around 70 participants who have presented their research articles in the online as well as in the offline mode. It was very meticulously arranged in 5 online seminar halls, and we have received feedback from the participants also about the wonderful arrangement. So with this recap, let me also say a small quote for this audience from Dr. APJ Abdul Kalam. To succeed in your mission, you must have single-minded devotion to your goal. So with this quote, let me welcome all of you once again to the second day of this international conference. Welcome you all.
Thank you, sir, for your welcoming the convention with your unfailing smile. And also, we thank you, sir, for the chief guest. An interesting quote of Phil Fargo echoes us as intelligence is knowing the right answer, and wisdom is knowing when to stay in.
So, hereupon, with overwhelming respect and admiration, we invite the wise intelligent Dr. Suraj Kiyavu, Professor and Head of the Department of Chemical Engineering Faculty of Engineering, Chulalongkorn University, Bangkok, Thailand. Truthfully, he knows a lot. In that way, he is a matchless intelligence. In addition, he waits eagerly to share his priceless knowledge with us. That way, he is wise. Therefore, with the thundering applause, let us welcome Dr. Suraj Kiyavu to present the keynote address.
Thank you. I hope that you can hear me clearly. All right, so let me share my
Yes, sir.
slide.
It's audible, sir.
Yes, sir. You are audible.
Well, I have problem with just one moment. I try to share my screen. Can you see my slide?
No, sir.
No. Oh, we have problem now. So, soon a minute. Sorry, I admit that. Wow, this is the first time for me to use Google Meet.
Sir, on your screen, you can find a small square box with an arrow.
Yes, that one, it's
Please click
visible
that one.
already. Yeah, I clicked that one and I try to share it, but now it's disabled already. Well, allow me to just, yeah, maybe I have to leave and come again.
Share this. Let everyone share this.
Hello? Okay. All right, so wow, now I changed the browser already. Just try again. One moment. Okay, I hope you can see my slide now, right?
Yeah, it's coming, sir.
Yes, sir.
Okay, yeah, good, very good. So thanks again for inviting me and for a nice introduction.
Sir, could you move your next slide, sir?
Now you can see my slide. No.
Ah, yes, sir. Yes, sir.
We are
We are
ready.
seeing. Just we are checking.
Okay. Yeah. Let us check first. It's moving.
Ah, yes, sir. Yes, sir. It's moving.
Moving. Yeah.
Yeah, you can.
Yeah. Very good. Very really good. So, and my voice is also clearly right.
Yes, sir. Yes, sir.
Okay. Thanks again for the organizer for inviting me and for a nice introduction. Allow me to start my talk by showing this magnificent photo of our campus. You see that the campus is surrounded by tall buildings as our campus is located in the heart of business district of Bangkok. At the center, it is our main auditorium. And well, if we look at our planet from space during the night, we see many bright spots, indicating that the place where electricity consumption is intense. When you see light, you see the modern world, and where you don't, there's one of two conditions. Either nobody lives there or it has not been electrified. For such a case, there's no more precious gift you can give those people than electricity and access to electricity. But we want sustainable electricity, and there is going to be carbon-free electricity. Wind, solar, but they are intermittent and they are incapable of being base load, fully integrated to the power grid. Energy storage is a key. In terms of cost, you see the solar and wind win the rest, and they are about 3 times cheaper than biomass. However, as we have to respond to the question, what should we do when the wind is not blowing and the sun is not shining? And yes, energy storage is the key. Though technologies regarding harvest and conversion of renewable energy are significantly advancing, we can effectively produce electricity via wind turbines and photovoltaic cells at a fraction of cost. We can produce electricity and feed to the power grid. However, there's no inventory in power grid. Even we install more PV, but we cannot respond to the electricity need during the nighttime. To address this issue, we need energy storage system. In terms of cost, a pumped hydro energy storage system, we call it PHES, is the cheapest option. However, PHES require high initial investment. Also, installation of pumped hydro energy storage system is geographically limited. Electrochemical energy storage, such as rechargeable batteries, is preferable. Batteries need 2 electrodes of different potentials. Basically, batteries store energy in a form of chemical energy and convert to electricity. I'm sure everyone here has used batteries before. You are probably familiar with alkaline batteries. Unfortunately, alkaline batteries cannot be recharged. There are several attempts to make alkaline battery rechargeable, but they are in an early stage. So alkaline batteries are not our target because we cannot use these batteries to store electricity generated from PV or wind turbines. Well, there are several technologies for rechargeable batteries. The common technologies are lead acid battery, nickel cadmium batteries, lithium ion batteries.
கேட்கல வெளியில இருந்து வந்தாங்க நல்லா இருக்காது பாக்க.
Sorry? Okay, I continue my presentation then. There is one thing in common between these technologies. Each cell has a specific energy and specific capacity. That means power and capacity are not independent. For example, if your application needs certain power but double capacity, you need to double the number of cells. Thus, for large capacity application, the cost goes linearly with the capacity. Now you get the concept. You see that for such the case mentioned earlier, The active materials are packed inside the cell. We call this configuration an enclosed battery. Instead of packing active material inside the cell, if we allow the active materials to flow through the cell, we call this configuration a flow battery. If we need larger capacity, we do not have to increase the number of cells. We just increase the size of the storage tank. From this viewpoint, it is clear that the power and capacity are independent. For small single cell, it looks like this. Okay, on your left-hand side, this one is a vanadium redox flow battery. We have two separate tanks of anolyte and catholyte. The flow battery is targeted for very large capacity application. And because the power is independent from capacity, low cost is the advantage. Moreover, this system has a very long cycle life. Another configuration is a hybrid flow battery. In this configuration, power and capacity are not totally decoupled. For example, zinc air battery, zinc bromine battery, and zinc iodine battery. In zinc air flow battery, the electrolyte containing zinc cation is fed to the cell. When we change the battery, zinc cation is reduced and deposited onto the electrode. So it is apparent that the space on the electrode limits the capacity of the battery. So let me conclude. Batteries are a storage system for electrons. We need two electrodes having different electrode potentials. Of course, highly reversible reaction is preferable. If we want to build battery having very large capacity, we cannot rely on scarce or rare materials. If your technology uses rare metals such as platinum, later you will have problems when we scale up the system. In my lab, I won't allow my student to touch it. Zinc has been used in batteries very long time ago. In primary batteries, we have zinc carbon, alkali batteries. Both systems are very common. Both systems use zinc and manganese oxide as active materials. For zinc carbon batteries, ammonium chloride solution is used as an electrolyte. In comparison, potassium hydroxide is used in alkali batteries. Though the production and consumption of zinc carbon and alkali battery are huge, we do not much pay attention to primary batteries. We focus on secondary batteries. There are a number of possibilities for rechargeable zinc-based battery. They are rechargeable alkali, zinc nickel, zinc air, zinc bromine batteries. Zinc ion batteries are also under development and receive much research attention recently. We start from zinc ion batteries first. This one can be fabricated as enclosed battery cells. Similar to lithium-ion batteries, zinc-ion batteries are a rocking chair battery, where the charge storage process depends on the transport mobility of zinc ions between the cathode and anode. There are four main energy storage mechanisms in zinc-ion batteries. First, insertion extraction. Second, displacement intercalation reaction. The next one is anion redox conversion, and the last one, dissolution deposition of zinc. So the charge storage mechanism of zinc ion battery rely on two processes, namely the intercalation, de-intercalation of zinc ions at the cathode, also called intercalation material, and the dissolution deposition of zinc at the anode. Theoretically, zinc as an electron source can deliver a large capacity, very huge capacity of around 820 milliamp hour per gram via dissolution reaction. In most cases, the capacity of zinc have been limited by the lower capacity of host material. To that, several kinds of host material have been undertaken in the study of zinc-ion battery. Several aqueous zinc-ion batteries, we call AZIB in short, recently proposed are seen to be very promising both in terms of performance and cyclability. However, up to now, no zip have been recommended for the commercialized battery market. This outcome points to the fact that there are a number of barriers which limits their application in practice. The issue within the aqueous zinc-ion battery system are as follows. The first one is hydrogen evolution reaction. Since water is a protic solvent which can dissociate and provide proton, the contribution of proton upon charging is unavoidable. Thus, the proton charging efficiency and excessive pressure within the battery package. In practice, the high concentration of zinc salt as well as the addition of some inhibitor can suppress the hydrogen evolution reaction. And the second one, dendrite formation. Dendrite formation is not such a new issue in battery researches, especially in the system where metallic anodes are used. In aqueous zinc-ion battery, zinc dendrites can be formed due to the uneven zinc-ion flux and electric field above the zinc anode, and can lead zinc-ion battery to failure because of short circuit. And the next one, corrosion of zinc. We call it self-corrosion of zinc. Is a different scenario from hydrogen evolution reaction due to the fact that aqueous mine acid electrolytes always contain protons, and the proton has a higher standard potential than zinc. These protons can draw the electron from the metallic zinc. Accordingly, zinc is corroded and changed into the zinc ion, and then pressure is built up within the cell because of hydrogen gas produced. And the last one, passivation. One of the issue concerned in ASIP development is the zinc formation of a passive layer. Is the formation of passive layer, which can reduce the performance of a zinc-ion battery in long-term cycling. In the most widely used electrolytes such as aqueous zinc sulfate electrolyte, zinc hydroxyl sulfate, we call it ZHS, is found to be the main passivation species. So many approaches have been proposed to solve the issue I mentioned earlier, such as the inhibitor addition, the artificial solid electrolyte interface, the modification of zinc electrode. However, such problems cannot be entirely eliminated. 3 out of 4 issues mentioned in aqueous zinc-ion batteries studies involve the existence of proton. Accordingly, we believe that this issue can be avoided fundamentally by employing non-proton donor electrolytes or non-aqueous electrolyte. Due to their wide stability window, non-aqueous electrolytes such as organic electrolyte have been extensively used in lithium-ion batteries for more than a decade. In recent years, several efforts have been initiated to apply non-aqueous electrolytes in zinc-ion batteries. Most non-aqueous zinc-ion battery studies guarantee that the hydrogen evolution reaction and zinc corrosion can be effectively inhibited. Besides, non-aqueous electrolytes are stable enough to be used with high voltage host materials such as Prussian blue analog, cobalt oxide, polyanion type phosphate, and graphite. It is immensely important to clarify what is missing in the research in order to pave the way toward further development and to produce a clear understanding as regards the mechanism of non-aqueous zinc-ion batteries reactions. Here, an attempt is made to provide perspective with respect to the important issue and a benchmarking of a non-aqueous zinc-ion battery technology in order to make possible the enhancement of the system. Well, potential solvent choice for a zinc battery electrolyte is dimethyl sulfoxide. Dimethyl sulfoxide possesses several promising properties such as high dielectric constant, high donor number, wide electrochemical window, and low toxicity. To observe the cycling behavior of the and morphology of zinc for use in dimethyl sulfoxide or DMSO based electrolyte, a galvanostatic cycling test of zinc anode was conducted and shown here. You see that at the first cycle, it was found that the size of the deposition dissolution voltage for each sample was relatively large compared to the aqueous electrolyte. Then the voltage of the DMSO sample decreased continuously until a stable plateau was reached, and close to that of aqueous system. In terms of cycling stability, after 30 cycles, both DMSO-based electrolyte and the aqueous-based electrolyte were found to be very stable. This stable trend continued for at least 200 cycles. Subsequently, when deposition dissolution voltage of the aqueous sample was compared with the DMSO-based sample, a clear gap was found. This was owing to the slower kinetic reaction of the zinc surface within DMSO. And the morphology of zinc was found to be large boulder having several hexagonal-like structures. It is noted that these structures prove to be similar to those obtained in zinc sulfate aqueous system at high current density of 20 to 40 milliamp per square centimeter. Results confirm that no zinc dendrite growth took place. Interestingly, the morphology of zinc formed from non-aqueous electrolyte have no dendrite formation when the voltage is similar. And the current density obtained during deposition dissolution from non-aqueous electrolyte on DSO is lower than that of aqueous electrolyte due to their high charge transfer resistance. And for the battery cycling test, we perform the rate test first and followed by cycling test, then switch to rate test and cycling test again. And the specific capacity was found to be 120, 130 milliamp hour per gram of manganese oxide. Then it slowly decreased, okay, until it reached a plateau at around 500 cycles. And this result point to the degradation of the battery performance at long-term cycling, yeah, but it's much more stable than in aqueous electrolyte system. Air battery. Zinc air battery is a hybrid flow battery because we allow the active material, which is zinc and oxygen from air. In this case, oxygen from air. We allow oxygen from air to pass through the system. And this system is fabricated as hybrid flow battery. This system targets as very large capacity application. Zinc air battery, or we call it in short ZAB, shows high potential for large-scale energy storage. This system uses zinc and oxygen directly from the ambient air as active material. So we use zinc to store electrons. Once the battery discharges, the electrons are stored in the form of zinc oxide. The underlying reaction for discharging process involves oxidation of zinc at the negative electrode and reduction of oxygen, so-called ORR, oxygen reduction reaction. During charging, zinc is reduced back and deposited at the negative electrode. And at the positive electrode, we have oxygen evolution reaction, in short, OER. Typically, we use alkaline aqueous electrolyte. Moreover, both zinc and zinc oxide are solid, so handling these species are not an issue at all. Those ZAB exhibit high potential for various energy applications. However, several barriers impact the practical application of rechargeable ZAB. Our group has focused on overcoming this issue via different strategies. Passivation of zinc electrode with zinc oxide, which is discharge product. Shape change and migration as the charge-discharge cycle continues. Dissolution and deposition of zinc repeatedly occur. Zinc tends to deposit at different locations and in different morphology. This issue affects performance and stability of the batteries. And the next one, dendrite growth. This is notorious issue of zinc electrode. At high current density, especially in alkaline electrolyte, or in condition where zinc deposition is limited by mass transfer, zinc tends to deposit in a form of dendrite and penetrate separator, causing short circuit. And the next one is corrosion of zinc. Zinc can react with water and produce hydrogen, okay, similar to in case of a acid neutral electrolyte in zinc ion battery. And the last one, zinc-case crossover. We have this issue in alkaline system, but not in neutral or acid system. Zinc-case crossover, the discharge product is zincate, right, of the system, and it can transform to zinc oxide. If zincate ions move across the cell to the air electrode and precipitate into zinc oxide at the air electrode, the zinc oxide can block the air channel or passivate the active site of the catalyst. Our group work on these issues using different strategies, such as using flowing electrolytes, developing modified anode for passivation inhibition, using electrolyte additives, and even developing an ion exchange membrane. These are some of our work addressing the issue. Okay, you see DOI on the right hand side. And the positive electrode of the system, or we call it an air electrode, is also very significant. OR and OER are involved during discharging and charging processes. Actually, these OR and OER are common in different energy devices. For example, in fuel cell, half of the system is ORR, right? Oxygen reduction reaction. Electrolyzer and carbon dioxide reduction system, half of the system is OER. Both reactions are sluggish and has high over potential. We need electrocatalysts for both OR and OER. Typically, OR electrocatalyst is not stable in oxidizing condition. Also, OER is not stable in reducing condition. We can use noble metal, but it's too expensive. Okay, and metal oxides such as manganese oxide is in certain phase and form exhibit excellent OR performance in strong alkaline electrolytes. We are also working on metal organic framework and covalent organic framework. You can refer to our recent article in journal Material Today Chemistry. You can refer to for OER, ruthenium oxide and iridium oxide are both excellent catalysts. However, again, they are both too expensive. Metal oxides show acceptable performance. Our group is working on layer double hydroxide. Layer double hydroxide are excellent OER catalysts, and they can be fabricated as self-supported structure, which exhibits excellent stability. Our recent article on layer double hydroxide can be found here in Journal of Alloy and Compound. Besides the catalyst, structure of the air electrode is also significant. Generally, the air electrode consists of gas diffusion layer and catalyst layer. As OR is three-phase reaction, we have to manage hydrophobicity and hydrophilicity of the electrode. Our group is working on tri-electrode configuration of zinc air batteries. We use separate electrodes and for charging and discharging and common zinc electrode. The system exhibits excellent stability and for charge and discharge. Moreover, we can optimize OR and OER catalysts independently. The cell we are currently developing can discharge stably even at 100 milliamp per square centimeter, and now we reach the aerial capacity of 150 milliamp hour per square centimeter already. And the next system is mechanically rechargeable batteries. This system provides a remarkable solution to overcome electrical recharging issue, whereby spent zinc electrolytes and electrolytes are physically removed and replenished. In short, we call it ZAFC. This system is a refillable cell in semi-solid form that can be used to store electroactive components necessary for battery operation in a tank located outside the battery structure. Compared to other types of batteries, such as lithium-ion battery, this system offers greater flexibility in terms of energy and power decoupling. There is less mechanical stress on the electrodes, enabling the manufacture of long-lasting system. And this system can be scaled up economically for stationary large-scale application. Since mechanically rechargeable zinc air fuel cell are refuelable primary batteries, they can use relatively simple catalysts that operate only in discharge mode, avoiding problem of dendritic zinc deposition seen by most electrically rechargeable batteries. Moreover, in order to produce zinc pellet in the zinc regenerator, dendritic morphology is preferred above other morphology. And to evaluate performance of such system, which integrate zinc airflow battery and zinc electrolyzer, we develop a mathematical model. The following parameters were investigated: electrolyte flow rate, potassium hydroxide concentration, and zinc cation concentration. Design. The influence of the hydrogen evolution reaction on the performance of the system was examined. And upon investigation, it was found that potassium hydroxide concentration had a significant effect on the performance of battery. Further, it was noted that increasing potassium hydroxide concentration enhanced HER and reduced the current efficiency. However, the optimum potassium hydroxide concentration, which was about 6 or 7 molar, provided maximum energy. Increasing zinc cation concentration was able to suppress the HER and increase the current efficiency of battery because of the lessening of reversible potential difference between the zinc electrode and reaction and hydrogen evolution reaction. A model-based analysis is one of the effective approach for the study of zinc air battery. And this technique, however, requires reliable discharge data as regards parameter estimation and model validation. I recommend 2 articles that you can find high quality data for the discharge of zinc air battery. In the first paper, we provide the data required for the modeling and simulation of the zinc air battery. Each set of data includes working time, cell voltage, current, capacity, power, energy, and temperature. And in the second paper, you can find discharge profile of zinc air battery at different flow rates and currents. A generic dynamic model for zinc air battery is a key component for effective battery management and monitoring. Zinc air battery shows nonlinear behavior where the steady state gain is strongly dependent on operating conditions. The voltage characteristic of zinc air batteries and lithium-ion batteries are compared. It can be observed that the voltage profile of lithium-ion battery has a distinct slope for discharge voltage and a high slope for open circuit voltage. On the other hand, the zinc air battery possesses a very flat slope in its voltage profile for both discharge voltage and OCV. Regarding lithium-ion batteries, the differentiation of battery voltage with state of charge can be discriminated due to its intercalation-de-intercalation mechanism. Hence, the relation between the voltage and state of charge is regularly useful for state of charge estimation. On the other hand, zinc air battery adopt the mechanism of zinc and oxygen conversion, whereby their change of dynamics is slower than that of lithium-ion battery. Moreover, zinc air flow battery utilize flowing electrolyte, leading to a more constant electrolyte concentration. For this reason, the voltage state of charge relation of zinc air flow battery is very flat and difficult to be discriminated. It is even more challenging to estimate the state of charge of this type of battery. So this study aims to develop a dynamic model being capable of predicting the nonlinear dynamic behavior of a reviewable zinc air battery using linear parameter varying technique. And this linear parameter varying model is constructed from a family of linear time invariant model where the discharge current level is used as a scheduling parameter. And the developed model is benchmarked against linear and nonlinear model counterparts. And the next thing we need is an effective state of charge estimation. Okay, because it is essential for the development of battery management system. At present, the provision of state of charge estimation for zinc airflow battery is still at its very early stage of the development. And this work set out to develop the state of charge estimator for zinc airflow battery. The estimator is based on a linear parameter varying model integrated with an extended Kalman filter. Okay, let me conclude. So, well, I introduced you rechargeable zinc-based battery and also critical components for rechargeable zinc air batteries and also, well, zinc ion batteries. And overall, we are catalyst development for zinc air batteries and the system of the tri-electrode configuration of zinc air battery and mechanically rechargeable zinc air batteries. Okay, so thank you very much for your attention. And well, if you have any question, of course, I am more than happy to entertain. Thank you.
Thank you, Professor. Thank you very much for sharing your field of research is very interesting and very lot of application oriented. So I leave the hall for any questions or clarification.
And of course, my email is here. I show my email here. Well, later you can, if you have any question, of course, you can send me via email.
Participants, please note down the professor's email address in the slide. Saradeep.k@chula.ac.th.
Okay, thank you very much. Yeah.
Thank you, Professor. Thank you. Yeah.
Thank you.
Hope we will be in touch with you.
Yeah. Thank you. Thank you.
Thank you very much, sir, for your thoughtful and well-researched talk.
Now, the third technical session is about to begin. So we humbly request Dr. Anandar Singh, Assistant Professor of the Department of Physics, share the session. Respected speaker, Dr. Muthu Pandian, respected head of the department, respected professors, my dear students, very good morning to. I am very happy to introduce our speaker, Dr. Muthu Pandian, research scientist, photovoltaic devices laboratory, SSN Research Center, SSN Institutions, Chennai, Tamil Nadu. He is expert to grow bulk crystals by Solson and melt techniques. He is expert to grow single crystals for the applications of non-linear optical, ferroelectric, and thermoelectric, and perovskite solar cells, dye-sensitive solar cells, quantum dot sensitive solar cells, and nanomaterials. He has completed 24 research projects from various funding agencies like DRLS, CERN, DST, STRI, UGC, DAE, Canada, and the SSNI, worth of 318 lakh. He has published 160 articles in international journals. He has published 35 articles in international conference proceedings. He has published 279 articles in international and national conferences. He has published 20 book chapters.
He has organized 21 international and national conferences. He has visited 6 national laboratories. His research papers cited by 2,275 repeated articles. H index of his publications is 26. ITER index of his publications is 61. 5 students are doing PhD under his guidance. 6 PhD students, 14 PDF students, 5 JRF students, 4 SRF students, 11 JRA students were completed their projects. He received many awards like Sri P.K. Das Memorial Best Young Scientist Award, Sasi Raman Young Scientist Award, Asia Scientific Ranking Award, DAE Best Poster Presentation Award, Indian Spectrophysics Association Award, RSC Highly Cited Author Award. He is an editorial board member for many international journals like International Journal of Research in Science and Technology, International Journal of Medical Sciences and Technology, Oriental Journal of Physical Sciences, Frontiers in Regional Materials, ERK Journals, Journal of Innovative Novel Research. He is an associate editor for the following journals: Indian Association for Crystal Growth, Newsletter, Nanoscale Reports, Science and Technological Research Journal, Royal Book Publications. He is a guest editor for Chemical Physics Impact, Journal of Advances in Optoelectronics. He has membership for many professional bodies like International Organization for Crystal Growth, Indian Association for Crystal Growth, Review Committee in Solid State Physics Symposium, Review Committee in National Laser Symposium, International Organization of Scientific Research and Development, Taiwan. He is an executive member for Indian Science and Technology Association, European Science Association, IPOD Periodicals, Indian Spectrophysics Association. He is a reviewer for many journals of various familiar publishers like Royal Society of Chemistry, Elsewhere, Springer, etc. He has published chapters in many books like Crystal Growth and Characterization, Device Quality, and Bulk Size Non-Linear Optical Single Crystals by Rotational Sankarnarayan Ramaswamy Method, a new crystal growth method, investigations on crystal growth, structural, optical, and thermal properties of 2-amino nitropyramine derivative single crystals for non-linear optical applications. Wide outcomes on research and latest development, directional growth and physical properties of 2-amino 5-nitropyridine pinosulforate single crystal for non-linear optical applications. Interfacial engineering in functional materials for dye-sensitive solar cells, biomass derived carbon for dye-sensitive and perovskite. With this short introduction, once again I welcome Dr. Muthusandil Manian for his session. Thank you, sir.
Thank you very much for your nice introduction, sir. Very good morning. First of all, I would like to thank the convener of this international conference, Dr. Joseph Wilson, and organizing secretary, Dr. Raj, and other faculty members of this department for giving me this wonderful opportunity to share some of my recent research work in crystal growth for practical device application. So this is the title of my today's lecture: Development of Device Quality Nonlinear Optical and Ferroed Single Crystals. And we have grown a lot of single crystals, and we characterize and we use it for the applications. So growth of high quality with a large size with the higher physical properties, which means that the higher optical quality, higher mechanical stability, higher optical homogeneity, electrical conductivity, is still very challenging task for crystal growers by Solzhenitsyn method. So high quality single crystals is of great importance when it's come to the device making. So in this lecture, I am going to present you a method which gives you the crystals of very high quality So all the crystals, whatever you are going to see in my slides, are grown by three different solution growth technique, namely SCST, slow evaporation solution growth technique. In a beaker, small size beaker and crystallizer, we have grown several nonlinear optical and ferroelectric single crystals, and we used the same small size single crystals as a foundation in SR method. We have grown lot of unidirectional solution crystallization method. We have grown lot of technologically important single crystals. But in order to improve further the physical properties and the crystalline perfection, and we have done lot of modification in this conventional unidirectional SR method. It is called as a RSR and ISR method. So this is the outline of my today's lecture: introduction and importance of single crystals, and the crystal growth by conventional method, and its what are the drawbacks when we grow the crystals by its conventional method, and in order to avoid the several dislocation, and in order to improve the physical properties, and we have selected this unidirectional crystal growth method. And what are the advantages when we compare the crystal growth by this conventional method? Under identical condition, we have compared the physical properties by these two techniques, SCST and SR method. And we have done the imaging technique in RRK Tindu, and we have identified the convection and the concentration fields in the SR method. The growth phenomena we have identified using this imaging technique, and we have worked on the special material TGS ferroelectric single crystals. So below its TC, the crystal belongs to the ferroelectric nature. Above the TC, the crystal belongs to ferroelectric nature. For the first time, we have done this TGS crystal growth by its below and above TC, and we have done a lot of modification. As I told you, it is a rotational Sankaraya Ramasamy method and the immersible ample Sankaraya Ramasamy method, and we have checked the physical properties and the crystalline perfection of these two techniques with these conventional SR and SCST method, and we have successfully fabricated the type 1 type 2 SKG second harmonic generation device element from the grown crystal, and finally we have compared the physical properties and the crystalline perfection by these three different unidirectional methods, and I conclude my lecture. So single crystals forms an indispensable part of rapidly advancing technology. The art of growing these kind of single crystals has turned into science with a variety of wide range of application. And a variety of single crystals find applications in lasers, nonlinear optics, LED, pyroelectric, piezoelectric detectors, optical components, and so on. So the availability of this kind of single crystals is equal to the ability to rise the country's economy. The ability to grow this kind of technologically important single crystals is an essential criteria for the competitiveness of our nations. So these are the normal nonlinear optical and ferroelectric single crystals grown by this unidirectional method. Some of the crystals are as grown crystal, and these are the cut and polished wafers for applications. Now we are going to see some of the practical device application of these grown crystals. We all know this quartz crystal is used in your watches, and these are the possible lithium niobate single crystal application. It has been used in a piezoelectric gas lighter, optical data storage technology, telecommunication industries, and eye treatment through laser. These are some of the application of piezoelectric materials. It has been useful in the medical ultrasonic transducer, NDT detector, piezoelectric transformer, underwater transducer to identify the tsunami. And these are the cut and polished BBO and LBO single crystal, and this has been useful for the frequency conversion devices. Indeed, it also produces the lasers. So crystal can be grown from solution, melt, and wafer technique, in which solution and melt techniques are most commonly useful for any kind of practical device application. These are some of the invention of crystal growth method from 18th century, hydrothermal method, Bernoulli, Jagrodsky, Bridgman. There are a lot of melt growth, solution growth, and wafer growth techniques are available to grow the technologically important single crystals. In the present investigation, I am mainly concentrated only on these two different methods, SCST, slow operation solution method, and unidirectional SR method, and invented by Professor K. Sankaranarayanan and Professor P. Ramasamy when they worked in the Alagappa University, Karigadi. So far, by this method, more than 300 numbers of crystals have been grown, and we can able to grow the positive soluble material, negative solubility material, organic, inorganic, semi-organic, low soluble, high soluble. All kind of crystal can be grown by this SR method. These are the classification of nonlinear optical single crystals. So we can grow organic, inorganic, and semi-organic material. the main advantages of these organic single crystals is we can grow the highly efficient single crystals, but due to weak van der Waals force, we cannot able to get the very high large size single crystals and unidirectional single crystals by this organic method. But in the case of inorganic, we can able to get the large size single crystals, but the problem in these inorganic materials, we cannot get the highly efficient material. So in order to get the advantages from organic and inorganic, now crystal growth researchers are working and growing lot of single crystals in semi-organic material for SHG and ferroelectric application. These are some of the properties needed for the nonlinear optical single crystals. So before you select the any material, and you have to concentrate on these parameters, should be high nonlinear optical coefficient. For laser application, one must know the laser diameter threshold value of the ground crystal. So we have to identify the laser diameter threshold value of the ground crystal, and fast optical response time, wide transparency range in the range of UV, visible and IR region, 200 to 1100 nanometer. The optical transmission should be very high, and it should be high thermal stability. So if you give the crystal for practical device application, we have to make it as a very thin plate or very big size crystal. So we have to polish the crystal. So before we go for polishing, we have to identify the mechanical stability of the ground crystal should be very high mechanical stability, otherwise the crystal will be damaged, and it should be very high chemical stability. Ability to process into the crystal and the device fabrication steps should be very easy. So these are some of the conventional method grown 2-amino 5-nitripridine derivative single crystal supported by DSC SCRB, Science and Engineering Research Board, Government of India. So our ultimate aim is to grow the unidirectional these 2-amino 5-nitripridine derivative single crystals along its SKG direction. So these are some of the crystals grown by conventional method in a crystallizer, small size crystallizer, and we have prepared the 1 liter solution and we have poured in the solution, and when the solvent is evaporated, the remaining solid particles are growing as a single crystal. But the problem is we cannot use it as it is for the practical device application because of the very small in size. Also, you see, because of the temperature fluctuation of the daily variation, there are a lot of solvent inclusions are trapped in the ground crystal. You see, many of the single crystals are having this kind of issue like solvent inclusion, milky opaque, and microcracks also formed in a lot of conventional method ground crystal. But like these 2-amino 5-nitripridine, beta-toluene sulfonic acid, this bromic acid, single crystals are having very high SHG efficiency comparable to the standard potassium dihydrogen phosphate single crystal. At least more than 50 times greater than that of the standard KDP single crystals for laser application. So the material is very high efficiency. The internal properties will not change, but the physical properties due to temperature fluctuation, solvent inclusion, microcracks, milky opaques, so it suppresses the physical properties. So we cannot get the highly physical properties with good crystalline perfection in conventional method. In order to avoid this issue, we have identified this unidirectional method and we have grown the same crystal. You see the small, the crystals grown by this conventional method, and we have selected as a seed crystal, and we have mounted at the bottom of the glass sample, and we have grown successfully the same 2-amino 5-nitripridine derivative single crystal by this unidirectional method. These are the as-grown crystal, and these are the cut and polished wafers along its SKG direction. So several attempts have been made to grow the crystals by this slow solution method like slow operation method, slow cooling, seed rotation, and melt growth technique like Bridgman, Zegralski, float zone, zone melting, and flux growth method. All the reported methods are at an elevated temperature that leads to thermal induced growth defects and complicated equipment, difficulty in growing large single crystal, and multi-step processes are also involved. And these are the ammonium tartrate single crystals grown by conventional method. This is the morphology, and this is the AMP4N single crystal, 4-nitripridine derivative single crystals grown by the conventional method, and this is the morphology. And these are some of the 4-nitripridine derivative single crystals supported by DAEBRNS, Department of Atomic Energy, and we have successfully grown lot of large size unidirectional the same crystal by this unidirectional method. And this is the trisol derivative single crystals grown by conventional method. You see, there are a lot of solvent inclusions is trapped in the grown crystal. The lot of milky opaques and microcracks are also formed in the conventional method grown crystal. And these are the conventional method grown several nonlinear optical and ferroelectric single crystals for applications. And these are the disadvantages of this conventional method grown crystal. Due to temperature instability, and the multinucleation will be formed in the grown crystal, and several microcracks are appeared during the growth, and the milky effects are also appeared in the growth. This is the sulfamic acid single crystal grown by conventional method, and we cannot get the single and bulk size single crystals when we select the SCST method. And these are the Grosseter boundaries. There are a lot of Grosseter boundaries are appeared in the conventional method grown crystal, and it has been reported that the dislocation density of this conventional grown crystal is very high because of these Grosseter boundaries, and the uniformity of this conventional is less, and the due to solvent inclusion, entrapment of solvent inclusions in the crystalline matrix, and there are a lot of long grain boundaries that appeared in the conventional method grown crystal. So not only the sulfamic acid, almost all the conventional method grown crystals are having these kind of issues. So this is the 4-interferon derivative single crystals for nonlinear optical application. If you concentrate any one single crystal, all the single crystals are having different planes, facets, growth sector, and growth sector boundaries. But for application point of view, phase matchable portion is only useful, and other portion will be cutted after cutting the phase matching angle. For devices like frequency doublers and optical parametric amplifiers, phase matching needs to be achieved. Otherwise, the conversion efficiency would be very low. So in this point of view, this SR method has given the solution, and it is possible to grow the crystal along its phase matching direction, or along whatever direction you want, you can grow by this method. If you wish to grow the crystal along its A direction, B direction, or C direction, you can grow by this method. So this is the diglycine bearing blood dyed single crystals, nonlinear optical material grown by conventional method. The same crystal we have mounted along its C direction, 001 dominant plane, and we have mounted at the bottom of the glass sample, and we have successfully grown this much of large single crystal by this SR method. And this is the SSDG, sodium sulfide dihydrate single crystals grown by conventional method, and this is the cut and polish efforts of the same material grown by this SR method. So just for your understanding, I have included this slide. This is the morphology of this KDP, potassium dihydrogen phosphate single crystal for laser application. So the phase matching direction of this KDP is 59 degree. So what we have to do is we have to cut the crystal along its 59 degree. First, you have to identify the single crystal X-ray diffraction morphological measurement. You have to identify the phase matching direction, and you have to cut along its phase matching direction, and you have to mount at the bottom of the glass sample. Then you have to pour the saturated solution. Then temperature we have to apply for solvent evaporation. So this is the SKG directed KDP single crystal, and this is the green emission in the KDP single crystal grown in RRK Tindu. This is the same KDP potassium dihydrogen phosphate single crystal grown in our laboratory, SSM. So this is the same crystal. This is the crystal 2-amino 5-nitrophenol 4-nitrophenol single crystals grown by SCST conventional method. In a crystallizer, we have grown this single crystal. The same seed crystal we have mounted at the bottom of the glass sample, and we have grown this much of large single crystal by this SR method, Sagana Ramasamy method. But still, there are a lot of impurities are segregated in the SR method grown crystals. So in order to avoid this issue, so we have made a lot of slabs and tubes on the SR glass sample, like a lot of holes we have made along its direction, and we have completely rotated the glass sample with the solution and the seed crystal so that the impurities are pushed out from the glass sample, so one can minimize the impurity segregation in the RSR method grown crystal. So if the impurities segregation is less in the grown crystal, naturally the physical properties will be higher and the crystalline perfection will be higher comparable to this SR and the conventional method grown crystal. And we have grown this the same crystal by ACRT method, point seed rotation technique, and we have successfully fabricated the type 1 type 2 SKG element from the grown crystal. So this is the TGS crystal. As I told you, we cannot grow the use the entire crystal for the application. So only this polar B direction. So the polar B direction in the conventional grown crystal is very small size. So you have to identify the thin layer of this polar B direction, and you have to cut and you have to mount it at the bottom of the glass sample, and this much of large single crystal can be possible by this SR method. This is again the glycine phosphate along its polar B direction, and we have grown this much of large single crystal. So the crystal growth technique for the present investigation, I mainly explain the growth and characterization by using this SR method and the conventional solution growth method. So before you go for that longest unidirectional growth, we have to identify and we have to carefully choose all these parameters. That is the instrumentation, synthesis, and conventional crystal growth, and the selection of different seed crystal direction, whether you used to grow the crystal along its A, B, C direction or different place, or if it is a non-centrosymmetric material, and you have to identify the phase matching direction, and or if it is a ferroelectric material, you have to identify the polar B direction. So before you mount the seed crystal, you have to confirm whether the direction of the grown crystal. And different sizes of the glass sample, it depends upon the solubility of the material. If it is a very high soluble, one can able to get the large size single crystal. So you can select the large size ID and OD, so inner diameter and outer diameter of the glass sample. If it is a very low soluble, and you can get the very small size single crystal, so you have to choose the very small inner diameter of the glass sample. And unidirectional crystal growth and growth optimization means you have to apply two different temperature at top and bottom portion, and top is for the solvent evaporation. So at a different temperature with identical seed crystal like 40 degrees Celsius, what is the growth rate? 41, what is the growth rate? 42, what is the growth rate? If it is a new material, you have to identify yourself with the different solvent with the different temperature. And finally, the growth rate measurement. This growth rate of the grown crystal depends upon what is the temperature you have selected at the top and bottom portion, what is the glass sample you have selected at the top and bottom portion, inner diameter and outer diameter, and what is the direction, seed crystal direction you have selected. And the experimental setup of this SR method consists of the glass sample, and then this glass sample is kept inside this water bath, and a thin plate like a seed crystal mounted at the bottom of the glass sample. Then you have to pour the saturated solution inside the glass sample. So after a few hours time, due to gravity-driven concentration, all the solid molecules are approaching the crystal surface directly. So this crystal surface attracts more atoms very easily. So the concentration at the bottom portion is very high compared to this top portion. And then you have to apply the temperature, Kandal wire coated the temperature at the top and bottom portion. There are small wire connections are there with the ammeter, transformer, and RTD sensor, and RTD temperature controller. And you have to carefully connect the temperature controller. Otherwise, if any small temperature fluctuation will be happen, then we cannot get the large size good quality single crystal. So the multinucleation will be formed, and the micro cracks also will be formed due to temperature fluctuation. So you have to be very careful when we select the temperature at top and bottom portion. And the top of this temperature is only for solvent evaporation, and this bottom of this temperature is for growing crystals. So only the thing is, and you have to select the uniform temperature near the seed crystal and the solution interface. You have to maintain the uniform temperature. And to avoid the temperature fluctuation of the daily variation, and the water is frequently added inside this water bath, you have to maintain the water level, otherwise you cannot maintain the temperature at top portion. And freshly prepared saturated solution is frequently added inside this glass sample in order to avoid the fungus formation in the SR grown crystal. So after few weeks or few months time, depends upon the solubility of the temperature, solubility of the material, and the temperature what you have selected at the top and bottom portion, and the diameter of the glass sample, the crystal will be grown like this. So this is the diglycine barium chloride monohydrate single crystals for nonlinear optical application. So this is the complete animation we have this SR method experimental setup. So this is a selection of seed crystal cutting and mounting. So this is the ferroelectric TJ crystal, and you have to identify the direction, polar B direction, and using the sharp axe blade and frame, you have to cut like this, and you have to make it as a very thin plate like a seed crystal, and you have to mount at the bottom of the glass sample, and then you have to pour the saturated solution as I told you in the animation slide. And this is a schematic view of this SR crystal cutting and mounting. This is the actual crystal growth of the TJS crystal. You see the polar P directed TJS crystal is mounted at the bottom of the glass sample, and this is the water bath, and this is the glass sample, and this is the transparent single crystal, bulk single crystal grown by SR method. This is the TJS saturated solution. And what are the advantages of this SR method? So single crystal with specific orientation in a glass sample. So this is the TGS crystal along its A, B, and C direction. So whatever direction you want, you can grow by this method. And this is the lysine monohydrate single crystals. So easily we can find out the growth rate along any plane. So if you wish to identify the growth rate along single crystal with a different plane, you have to identify the growth rate means you have to cut the crystal along different direction under identical condition means under identical thickness, identical saturated solution, identical glass sample size, then you have to measure the growth rate along different plane. So the 100% solution to crystal convertibility is possible in this method. So the entire quantity of the solution is converted into the crystal. So this is the 20 centimeter longest TGS crystal along its polar B direction. You see there is no microcracks and milky opaques. The transparent, this much of large single crystal can be grown by this SR method. So with a thin plate like a seed crystal, this much of large single crystal can be possible. So with a 2 mm thickness of the grown crystal by conventional method, around 9 centimeter length and 2.5 centimeter diameter of these SSD single crystals have been successfully grown. A lot of crystals have been grown. So the scaling up was relatively very simple by this method, and this is the benzophenone organic single crystal using xylene as a solvent for the nonlinear optical application. Normally, in conventional method, the crystal will be grown like this. So if suppose the SKG direction of this crystal is this is the morphology of the KAP, potassium acid thalate single crystal. Suppose this is the SKG direction or this is the SKG direction means you see the nucleation is started here in one first day, and this is the second day growth, and this is the third day, and this is the fourth day, this is fifth day, sixth day, seventh day. You see there is no uniformity in the growth of the crystal by the conventional method. So there will be naturally no uniformity optical homogeneity in the conventional method grown crystal. But in the case of SR method, it is a layer by layer growth like this. It is a layer by layer growth. So comparable to this previous one, conventional method, the uniformity and the optical homogeneity of the grown crystal is very high, superior compared to this conventional method grown crystal. And this is the sodium chlorobromoaxide single crystal along its A direction reported by in one Chinese laboratory. And he has confirmed that the uniformity of this SR grown crystal is superior compared to this conventional method grown crystal. And the requirement of large size crystal chamber is avoided in this method. So if you wish to construct this SR method in your UG laboratory, PG laboratory, or PhD laboratory, so within 5 to 6,000 rupees, one can be able to construct the entire experimental setup in your research laboratory. For that, you need this 1 feet cross 1 feet glass bath, water bath. This water bath is nothing but usual fish tank only, and then this glass ampoule and two temperature controller. One is at top portion and one is at bottom portion, and this is directly connected to these two RTD controller with the RTD sensor and two ammeter and two transformer. So within 5 to 6,000 rupees, you can easily buy and you can construct in your laboratory. So this is a conventional method grown crystal. In a beaker, we have grown this crystal, and the same crystal we have mounted. So small thin plate like a seed crystal we have mounted, and we have grown this much of large single crystal. This is the as grown crystal, and this is the cut and polished wafers. So not only cylindrical shape depends upon the shape of the crucible. Any kind of shape can be possible by this method. So rectangular, triangular, prism shaped, all kind of shapes can be possible by this method. This is the organic benzophenone single crystal by this SR method. And this is the crystal without glass ampoule. This is the crystal with glass ampoule. And his Professor P. Ramasamy here is holding the organic benzophenone single crystals. So this method, large size crystal can be grown by this method for nonlinear optical application. So a thin layer of solution is in between the crystal and the glass ampoule. So there will be naturally no mechanical stress will be in the grown crystal. So length to breadth ratio can be varied at with a stoichiometric solution. So this is the normal conventional method grown KDP, potassium dihydrogen phosphate single crystal. When we grow the crystal in a crystallizer or beaker, so normally the morphology will be like this for the KDP single crystal for laser application. But depends upon the pH of the solution, whether if you wish to increase or decrease the pH of the solution, one can increase or decrease the growth rate along different direction. So this is the crystal grown by conventional method. This is the pencil shaped, this KDP, potassium dihydrogen phosphate single crystal using the SR method. So crystals which have post-go cracking tendency can be grown without resulting the post-go cracking tendency. So this is the conventional method grown crystal. You see there are a lot of microcracks and milky opaques are formed in the conventional method grown crystal. because of the temperature fluctuation of the daily variation. The solvent is entrapped in the ground crystal, so naturally the microcracks and milky bakes will be formed in the ground crystal. But in the case of SR method ground crystal, and we have maintained the uniform temperature at top and bottom portion, there is a stable supersaturation, uniform growth rate, and a uniform evaporation rate. There is no chance in the formation of solvent inclusion or milky opaques in the ground crystal. So the crystal quality is always superior to the conventional method ground crystal. This we have identified with the different physical properties, characterization, and chemical properties and crystalline perfection of the ground crystal using like HRXRD, birefringence, chemical etching, UV SNAR, Vickers microharness, dielectric, and so on. So far by this method, more than 300 numbers of crystals have been grown. So we can able to grow this kind of positive soluble material and a negative soluble material like lithium sulfate, and a low soluble material like KAP. You see, the low soluble KAP is 12.5 gram per 100 ml, and moderate soluble TGS 34 gram per 100 ml. And we can also successfully grown this high soluble, very high soluble material like benzobenone. So in a 100 ml of the solvent, 265 gram will be dissolved, and based on our experience in the SR method, and we have successfully grown the world's longest solution core crystal, and this is the low soluble KAP and moderate soluble TGS, and this is the negative soluble lithium sulfate, and this is the very high soluble benzobenone crystal. So the total length of this solution core crystal is more than 1 meter, 1350 millimeter, and 5.5 centimeter diameter. So in fact, this work was done in SSN, and we have initiated the world's longest solution core crystal in 2008, and we have successfully grown the crystal in 2011 with the different optimization at the top of the temperature with the different temperature like 40, 39, 42, and bottom of the temperature with the different seed crystal thickness with the different diameter with the help of Professor G. Bhavanarayana from the NPL New Delhi. And this is the experimental setup of this 8-feet SR method setup. And we have maintained the two temperature. One is directly connected to the top portion and then bottom portion. So when the crystal is growing from the bottom to top, we have to also increase the height of this controller from bottom to top. So this much of transfer and large single crystal can be possible in this SR method. And this is the morphology of this benzobenone single crystal. And we have selected this A direction, 100 direction for the longest growth, because the growth rate along this direction is very high compared to the all the other direction. So this is the different growth stages of this benzobenone single crystal. The seed crystal is mounted here, and then the roughness is started, then transparent crystal is started to growing. So this is the 850 mm longest benzobenone single crystal. This is the 1350 mm longest benzobenone single crystal, and this is the double diffraction pattern in the benzobenone single crystal. So similar way, we have grown lot of nonlinear optical and ferroelectric single crystals, and how to harvest the ground crystal from the glass sample. You see, this is the 20 centimeter longest TGS crystal along its polar B direction. In the experimental setup, we have maintained the two different temperature. One is at top portion. Normally, we have maintained the high temperature like 40, 41, 42 for salinity operation. And bottom of the temperature, normally we maintain just 1 degree above of the room temperature. So we cannot immediately stop this temperature top and bottom portion. Otherwise, because of the sudden fluctuation in the temperature, normally the microcracks and milky opaques will be formed in the ground crystal. And we have to reduce the temperature like 1 degree Celsius per day, 0.5 degree Celsius per hour, 0.25 degree Celsius per hour, depends upon the solubility of the material, and you have to reduce like this. And we have to wait until it reaches the room temperature. So once it reaches the room temperature, you have to kept out this crystal with the glass sample like this. And using this diamond wheel cutter, you have to remove the top and bottom portion separately. And this is the TGS crystal with the glass sample. And then using the glass cutter, you have to mark the top and bottom portion separately and very slowly. And you have to remove the glass sample very slowly. So this is the ferroelectric TGS crystal without glass sample. You see, this much of transparent crystal can be grown by this method. Then how to cut the crystal from the SR method grown crystal. So this is the diamond wheel cutter, and the ethylene glycol is kept inside this tray. And this is the speed controller. And you have to identify the mechanical stability of the ground crystal. So whether it is a low mechanical stable or moderate mechanical stable and mechanically very highly stable material. Then you have to select the speed of this diamond wheel cutter. You can increase and decrease the wheel cutter. And this is the cut portion of this TGS crystal, and this is the almost cut portion of this TGS crystal using this diamond wheel cutter. And this is the as grown TGS crystal, and this is cut portion of TGS crystal, and successfully cutted and sliced a lot of crystals using this diamond wheel cutter supported by DAE, Department of Atomic Energy. So this is the 20 centimeter longest TGS crystal at the bottom portion, and this is the middle portion, and this is the top portion. And this is the sodium sulfide diode single crystals for nonlinear optical application. And this is the cut and polished wafers. And this is the diglazing zinc chloride diode single crystals in a glass sample. This is the cut and polished wafers. And this is the 2 amino finite repeating derivative single crystals as grown crystal. And this is the cut and polished wafers. And this is the ferroelectric glycine phosphate single crystal. And this is the cut and polished wafers. And glycine phosphate cut and polished wafers. And this is the 2 amino finite pyridine beta toluene sulfonic acid single crystals. So normally in SR method we have evaporated the solvent and we have grown, but this is the different, and we have prepared the this saturated solution at 50 degrees Celsius, and we have poured in the glass sample, and we have maintained the constant temperature path, and we have reduced the temperature like 50 to 35 degrees Celsius with the 0.02 degrees Celsius per hour cooling rate, and we have successfully grown this crystal like this. And this is the low soluble KAP, and this is the ferroelectric TGS crystal and cut and polished TGS crystal, and this is the sodium para-nitrofenate single crystals for nonlinear optical application, and this is the conventional method grown crystal, and we have selected this 00 dominant plane for the SR method, and we have mounted here, and we have successfully grown this crystal, and this is the cut and polished wafers, and this is the diglazine barium chloride monohydrate single crystals. And this is the L-arginine 4-nitrophenol single crystals for nonlinear optical applications. And this is the ammonium tartrate single crystals for nonlinear optical application. So we have grown a lot of conventional method grown nonlinear optical and ferroelectric single crystals. And we have also grown the same crystal, and we have selected as a seed crystal, and we have mounted at the bottom of the glass sample. And we have successfully grown several unidirectional along its polar B direction, along its phase matching direction, along its C direction, dominant plane, and we have successfully grown a lot of the crystals by this SR method. Under identical condition, we have measured all the characterization. In order to check the structure of the grown crystal, first we have checked the single crystal X-ray diffraction, and we have confirmed the grown crystal. And in order to identify the crystalline perfection of the grown crystal, and we have measured the HRXRD, high resolution X-ray diffraction measurement. To identify the dislocation density, we have carried out the chemical etching measurement. For laser application, we have carried out the single and multi-shot laser diameter threshold measurement. For mechanical stability of the grown crystals, we have carried out the Vickers microharness measurement. For optical quality, UV NIR. For electrical measurement, dielectric permittivity and dielectric loss. For optical homogeneity, this Bayer-Vincenz measurement. So the samples crystal grown by conventional SR method were prepared with identical thickness for comparative purpose. The surface damage is affected by the energy absorbing defects such as stains, scratches, and polishing contaminants, which strongly influence the physical properties. Therefore, all the characterizations are performed on the highly polished crystal so that one can minimize the surface defects in the conventional SR method grown crystal. In order to confirm the reproducibility, so every characterization were repeated several times, and more or less similar results have been observed in the crystal grown by conventional and SR method. So this is the HRXD curve of the SR and the conventional method grown crystal. You see there are a lot of low angle grain boundaries are appeared in the conventional method grown crystal because of the solvent inclusion. So the entrapment of solvent molecules into the crystalline matrix is only responsible for appearing this kind of large number of low angle grain boundaries in the grown crystal. But in the case of SR method, you see single and sharp peak, which clearly indicates that the crystalline perfection of the SR method grown crystal is superior comparable to this conventional method grown crystal. And this is again the SR method SSDK single crystal, that golden color crystal, the 17 hours again with single and sharp peak. But in the case of conventional grown crystal, there are a lot of solvent inclusion, the microcracks, which clearly observed that the low angle grain boundaries in the HRXID curve. So the chemical etching is an important and powerful tool to identify the dislocation density of the ground crystal. So this is a diglazing zinc chloride a single crystal. You see from this figure one can easily calculate the SP density of the ground crystal. The formula is very simple, the number of H feeds divided by area. So manually you can calculate the number of H feeds and then area means the length and breadth, you can get the area. So number of H feet divided by area, you can easily calculate the H feet density, EPD of the conventional ground crystal is very high comparable to this SR method ground crystal. You see there are randomly distributed but strictly oriented HVs have been appeared in the conventional and SR method ground crystal. The number of H bits in the conventional ground crystal is high comparable to this SR method ground crystal because of the appearance of solvent inclusion, high number of dislocation density in the conventional method ground crystal. You see, this is for the 5 second and this is for the 10 second. So on successive etching for 5 to this 10 second, if you concentrate any one H bits, the H bits enlarge the size retaining the geometrical shape and do not disappear, suggesting that the bits are due to the dislocation. We calculated the approximate H bit density of this conventional ground crystal is 8.2 in 10 power 3 centimeter power minus 2, but in the case of SR ground crystal is very less comparable to the SEST method ground crystal, which clearly indicates that the crystalline perfection of this SR ground crystal is very high. You see, there are a lot of various type of defects are appeared in the conventional method ground TGS single crystal like solvent inclusions, low angle grain boundaries, micro cracks, milky opaques, microcrystallites, and so on. So not only the sulfamic acid and the TGS kind of crystal, almost all the conventional ground crystals are having this kind of issues because of the temperature fluctuation and the grosseter boundaries, grown band, and so on. So, but in the case of SR ground crystal, it is a single and morphological defined phases. So there will be less grosseter boundaries or no grosseter boundaries. So the dislocation of all the above causes are avoided in the SR method ground crystal. But in the case of conventional method ground crystal, that small size crystal, you cannot avoid the dislocation, the grosseter boundaries in the conventional ground crystal. And it has been already reported that the dislocations have been originated in the conventional method ground crystal along its growth sector boundaries and growth band. The mechanical stability of the ground crystal is identified using the Vickers Maker harness measurement, and this blue color indicates for the SR method ground crystal, and this red color indicates for the conventional method ground crystal. Because of the higher crystalline perfection, the mechanical stability of this SR ground, the large size crystal, is high comparable to this conventional method ground crystal. This is again the glycine phosphate, high mechanical stability comparable to this conventional method ground crystal. You see, because of the higher mechanical stability in the conventional ground crystal, there are a lot of micro cracks are appeared near the indentation. But in the case of conventional ground crystal, because of the lower mechanical hardness, the number of cracks appear near the indentation is less comparable to this SR method ground crystal. So this is that 20 centimeter long CTGS crystal. In order to check the mechanical stability along its bottom, middle, and top portion, we are carried with the Vickers micro harness. The mechanical stability along all these three portion is same more or less. So the less number of micro cracks in the conventional ground crystal is, so when the indenter lands on the surface of the material around it dissipates smoothly is the reason for less number of cracks in the conventional ground crystal. But in the case of SR ground crystals, more number of cracks because the flow of material under indenter cannot take place smoothly in the SR method ground crystal. So the reason for the high number of solvent inclusion and less mechanical stability in the conventional ground crystal is this only this solvent inclusion, and a variety of parameters such as variation in supersaturation and minor fluctuation in temperature, non-uniform growth rates are govern the solvent inclusion. This is the solvent inclusion pattern of the KCl and NaCl single crystal, potassium chloride and sodium chloride single crystal. These are the solvent inclusions appeared in the other conventional method grown nonlinear optic and furrowed single crystal. But in the case of SR method, we have maintained the uniform temperature under one single and morphological defined phaser and uniform solvent operation, uniform growth rate. There is no chance in the formation of solvent inclusion in the SR method grown crystal. And also in the conventional method, the growth is mainly due to the diffusion process. So the availability of material ingredient is less in the conventional method grown crystal. But in the case of SR method, due to gravity-driven concentration, the concentration at the bottom portion is high compared to the top portion. And we have carried out the single and multi-shot laser damage threshold value of the ground crystal, and because of the higher mechanical stability and the higher crystalline perfection of this SR ground crystal, so the laser damage threshold of this SR ground crystal is high, 17 millijoule per centimeter square, comparable to this conversion of the ground crystal, 12 millijoule per centimeter square. This is again the laser damage threshold value of this SR ground crystal is 19, and but in the case of conventional ground crystal is 15. And because of the lot of issues, dislocation density, solvent inclusion, micro cracks kind of issue, the laser damage threshold value of this SCST ground crystal is less. And we have calculated this dielectric tensor and dielectric permittivity of this SR method ground crystal. And this is the gold coated this material for the dielectric measurement. With this, we have done in RRK Tindu. So the dielectric permittivity of the crystalline material is a second track tensor. For orthorhombic crystal, there are 3 independent components. For monoclinic crystal, there are 4 independent components. So what we have done is we have identified the orthorhombic SSD gas, sodium sulfide diode single crystal, and monoclinic glycine phosphate single crystals, and we have cut the crystal along its 3 different direction, A, B, and C direction, and we have measured the dielectric permittivity and dielectric loss value of the ground crystal. And anisotropic in the dielectric behavior was observed in the SR method ground crystal, and this blue color indicates for the A axis, and this red color indicates for the B, and the green color for C axis. So the higher dielectric permittivity and the lower dielectric loss comparable to this conventional ground crystal, which clearly indicates that the optical transmittance and dislocation density is high in conventional method ground crystal. And this is that one interesting material, TGS, ferroelectric triglycerin surface single crystal. As I told you, the Curie point of this TGS is 49 degree. So below this temperature, this crystal belongs to the ferroelectric nature. This after this 49 degree, this crystal belongs to the parallel nature. And we have successfully grown the crystal along its this ferroelectric phase, along its parallel phase. At its TC, the crystal growth process is still going on. We are yet to grow the crystal. And we have successfully grown the crystal along its 2 different phases, and we have compared the physical properties and the crystalline perfection that you will see later. And then the optical transmittance of these conventional and SR ground crystals we have identified using the UV NAR measurement. So this is the surface of microscopic surface of this SCST conventional ground crystal. This is for the SR method ground crystal. You see, because of the high dislocation density, large number of solvent inclusion, micro cracks, milky opaques, the surface is more rough in the conventional ground crystal. But in the case of SR method ground crystal, it is smooth comparable to this SCST method ground crystal. And because of the no solvent inclusion, growth and the growth boundaries in the SR method ground crystal. So the surface is more smooth comparable to this SCST method ground crystal. And because of this lot of issues, the optical scattering centers are less in the SR method ground crystal, so that one can able to get the high output intensity. So if the high output intensity means the optical transmittance of this SR ground crystal is high comparable to this conventional ground crystal. This is again for the diglycine zinc chloride single crystal, higher optical transmittance comparable to this conventional method ground crystal. And we have also checked the optical homogeneity of the ground crystal using the Birefringence measurement. So in the case of SR method, we can easily control the growth boundaries, and we can avoid the solvent infusions, we can avoid the scattering centers in the ground crystals, we can avoid the micro cracks, milky opaques. So because of the no growth boundaries, the dislocation density of this SR method ground crystal is less. So the physical properties like optical transmittance, mechanical stability, dielectric permittivity, optical homogeneity of this SR ground crystal is high and superior comparable to this conventional method ground crystal. And we have also checked the crystalline perfection of the ground crystal using this HRXID, and we can identify the dislocation density of this SR ground crystal is less, very less comparable to this conventional method ground crystal because of the no growth boundaries, solvent inclusion, less scattering centers, no micro cracks, milky opaques, and less dislocation density comparable to this conventional method ground crystal. And we have done this optical imaging of convection and concentration field in interracial crystal growth using this highly soluble benzonine crystal. We have identified this growth phenomena of this SR method ground crystal. So we have performed the real-time and in situ optical imaging of concentration and convection field during the interracial growth of the benzonine crystal, and the shadowgraphic technique used to visualize the convection to quantify the thickness of the solidal boundary layer and the crystal growth rate along its C direction, and the maxillary interferometry is used to quantify the gravity-driven concentration profiles during the growth, and the parallel slided borosilicate crystallizer with the parallel slided outer chamber used for the imaging studies. The growth phenomena of these SR method grown crystals we identify using this experimental setup, and this is the three different growth stages of this benzoin crystal. So our ultimate aim is to identify the growth phenomena so near this transparent crystal and then solution interface. So this is scatography images of this SR method grown crystal, and this is for the 1 day, and this is for the next 5 days, and this is for the next 5 days, and this is for the next 5 days. You see at 6th day, there are a lot of plumes are started from the bottom of the glass sample. The plumes are nothing but the movement of fluid flow from the high concentration to low concentration. Then crystal growth is started at this 12th day. You see the transparent crystal is started growing from the bottom of the glass sample. If you concentrated any one plume, if you concentrate this plume, you see the plumes are started from the bottom of the glass sample near the seed crystal interface. The plumes are moving upwards, 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 up. Then finally the plumes are disappearing. Then new plumes are started from the bottom of the glass sample. From this observation, one can easily conclude that the gravity-driven concentration is only responsible for the growth of the crystal by this SR method. And as I told you, we have grown at its ferroelectric and paraelectric faceted, the TGS crystal, and this is the solubility at 30 degrees Celsius, 36 gram, at 54 degrees Celsius, paraelectric phase, 57 gram, and we have successfully grown the crystal along its below TC and above TC, and we have compared the physical properties like piezoelectric D3 coefficient and optical transmittance. You see, the optical transmittance of this paraelectric faceted TGS crystal is high, comparable to this ferroelectric faceted grown crystal, and a higher mechanical stability and a higher crystalline perfection of this paraelectric faceted grown TGS crystal, which clearly indicates that the ferroelectric faceted grown TGS crystal is very good for the higher data application, comparable to this ferroelectric faceted room temperature TGS crystal. And we have modified several things in the SR method. So when we say grow the crystal using the xylene, ethanol, methanol kind of solvent, so normally the multinucleation will be formed at the top of the glass sample. In order to avoid these multinucleations, we have introduced the glass blend, and we have successfully grown the crystal 2-aminophenyltryptamine 4-nitrogen derivative single crystal. And this is the crystal grown by conventional method, and this is the modified SR method. This is the cut and pulse wafers. And we have also grown the crystal by this fine seed rotation technique, 4-nitrogen derivative single crystal. And this is the crystal in a 2-liter solution container, and this is the 5-liter solution container. This much of large size crystal we have grown by this fine seed rotation technique. So this is the cooling rate of 0.1 degree Celsius, and we can slightly increase the cooling rate like 0.2 degree Celsius and then 0.5 degree Celsius. After this 0.5 degree Celsius per day, when we increase the cooling rate, the multinucleation will be formed. So this is the RTMS cooling rate of this 4-nitrogen derivative single crystals using fine seed rotation technique. This is the as grown crystal, and this much of large size crystal we have successfully grown by this fine seed rotation technique. And we have measured the UV linear transmittance in a 1-inch crystal, and we have successfully grown this much of large size single crystals with a transmittance of more than 90%. And we have fabricated the type 1 type 3 SKG element from the grown crystal. So when we grow the crystal by the SR method, we have used the several times recrystallization we have done, and we have used the same material to prepare the saturated solution, but still there are a lot of impurities are segregated at the top of the SR glass sample. So in order to avoid this issue, we have modified several things in the SR method, like we have made several slats in the SR glass sample and several tubes on the SR glass sample, and we have completely rotate this experimental setup of this RSR method, and this is the RSR method with slat, and this is the RSR method with the tube, and crystal is growing from bottom to top. See, it's mounted here and the growing. This is the 4-nitrogen solution, and this is the water bottle. So this is the different growth stages of this RSR method with the slat, and this is the RSR method with the tube. And this is the as-grown crystal, and this is the cut and polish wafers. So this is the crystal grown by the conventional method, and this is the crystal grown by the same crystal we have grown by this SR method. This is the RSR method, and this is the cut and polish wafers. So in order to check the crystalline perfection of this conventional grown crystal, you see because of the higher dislocation density and the lot of gross star boundaries, solvent inclusion, the crystalline perfection is not so good. The HRXRD full width at half maximum FWHM of this material is 56.5 hours again. The same material we have mounted at the bottom of the glass sample, and we have grown here. We can able to avoid the gross star boundaries of the grown crystal. We can also reduce the solvent inclusion, the micro cracks, milky opaques of the grown crystal, so that the crystalline perfection is slightly increasing here, 45.5 hours again in the SR method, but still there are a lot of impurity segregation happened in the SR method. So in order to avoid this impurity segregation in the SR method grown crystal, we have modified the this RSR method. Here we can able to control, minimize the impurity segregation in the RSR method grown crystal. So the crystalline perfection is very good in the RSR method grown crystal, 30 hours again. You see 30 hours again for RSR, 45.5 hours again for the SR, and this is not very good, 56.5 hours again for the conversion method grown crystal. So this is the comparison between the SR and RSR method grown crystal. Higher optical transmittance in the RSR method grown crystal, which clearly indicates the impurity segregation in the RSR grown crystal is less compared to the conventional grown crystal, and higher mechanical stability in the RSR method grown crystal, and a higher laser damage threshold in the RSR method grown crystal. So which clearly indicates that the RSR method grown crystals is superior for the practical device application. And this is the immersible amble SR method. Here we mounted the seed crystal at the bottom of the glass sample. We have maintained a lot of solution here, so we can grow the crystal by this slow cooling method. So this much of transparent large size single crystals we have grown by this ISR immersible amble Sangana Ramasamy method. This is the as-grown crystal. This is the cut and polished wafers. In order to check the crystalline perfection along its bottom, middle, and top portion, and we have identified using the HRXRD measurement. The crystalline perfection at its top, middle, bottom portion is almost equal in the ISR method grown crystal. So the final conclusion of my lecture is, we have identified the several technologically important nonlinear optical and ferroelectric single crystal, and we have checked the efficiency performance of this conventional method grown crystal, and we have grown successfully by SR method also. So if it is a non-center symmetric material, we have identified the phase matching direction. If it is a ferroelectric material, we have identified the polar B direction, and we have grown the crystal, same crystal by this SR method, and we have compared the physical properties and the crystalline perfection of this conventional and SR method grown crystal. And SR method grown crystals are having higher physical properties and higher crystalline perfection because of the no gross boundaries and no solvent inclusion, no micro cracks, milky opaques, and less dislocation density. But in SR method, some impurities are segregated in this grown crystal. In order to avoid this issue in the SR method, and we have modified this SR method by making lot of slats and tubes. We have introduced in the SR glass sample, and we have completely rotated the crystal in the RSR method so that the impurities are pushed out from the glass sample. So there in RSR method, one can be able to minimize the impurity segregation in the RSR method grown crystal. So naturally, when one control the impurity segregation in the grown crystal, the physical properties like mechanical stability, optical quality, optical homogeneity, and dielectric and the other physical properties are high and superior comparable to this normal SR and conventional method grown crystal. So the RSR method grown crystals are having higher physical properties and good crystalline perfection, which clearly indicates one can able to conclude the same RSR grown crystals can be useful for the nonlinear optical and ferroelectric application. So thank you very much for your kind attention. So if any doubt, I am very happy to respond. Thank you very much.
Thank you, Professor. You have given clear idea about conventional and SR method.
Thank you.
We have some clarification.
Yes.
Why you particularly used two different temperatures such as 30 degree and 40 degree for your SR method?
So this top of this temperatures, the purpose of the temperature we maintain at top position is only to evaporate the solvent. Just if we select the 1 feet glass ampoule, you pour the 1 liter solution. The aim is to evaporate the solvent at top portion. So when the solvent is evaporated, the remaining solid particles are approaching the crystal surface. We already mounted the seed crystal at the bottom of the glass ampoule with a different direction. We know that the direction of the ground crystal, the crystal will be grown like this. So at high temperature, top portion is only for solvent evaporation. At bottom portion of this temperature is only for growing, successfully grown the crystal. You have to maintain the uniform temperature at its crystal and solution interface. If it is any small fluctuation in the crystal and solution interface, so naturally in like conventional method, the multinucleation will be formed, a lot of micro cracks and milky opaques naturally will be formed in the SR method ground crystal also. For that purpose only, we have maintained the high temperature at top portion. So just to low temperature near the crystal and solution interface.
Sir, what method is generally used to encourage crystal to grow?
So if you have facility to grow the larger single crystal, you can easily develop the SR method in your laboratory. If you have only the beaker and the crystallizer in your laboratory, you can grow by SCST method, conventional method. Just prepare the saturated solution and you have poured the solution in your crystallizer and beaker, whatever you have in your laboratory, and just make it small holes at the top of this polythene cloth so that the solvent will be evaporated. You can get the crystal. But the problem in the conventional method, as I told you, because of the temperature fluctuation, so naturally the microcracks will be formed and the milky opaque. You cannot grow the single and large single crystals in the conventional method.
Do crystals grow at cold temperatures? Is temperature essential for crystal growth?
No, not. I'm not mentioning any particular temperature. If you grow the crystal by the conventional method, you have no choice. Only the room temperature you have to maintain the bath and you have to grow the crystal. But in the case of SR method, there is an option. You can increase the temperature or decrease the temperature because in SR method, the glass sample is kept inside this water bath. So you can vary the temperature at top and bottom portion, depends upon the solubility what you have selected.
Okay. Okay, thank you, sir.
Thank you.
Hardness. So I have a doubt, sir.
Yes, sir.
You used diamond indenter for
Yes,
the
sir.
hardness testing.
Yes, sir.
Have you tried with the ball indentation technique, sir?
Pardon, sir?
Ball
Diamond.
indentation technique. You use the diamond indenter to test the hardness of the crystal.
Yes, sir.
Have you tried with the ball indentation technique, ball indenter?
No, sir. No, sir.
What is the difference between that two, sir?
No, I don't know the other what you have mentioned, the bond indenter, but we have usually measured the mechanical stability of the ground crystal using Vickers Maker hardness only. So we just mount a crystal, we indent on the top of the surface of the ground crystal, we identify the diagonal length of A and B direction, and we easily measure 1.854 P by D square. With a different load, what is the indentation, diagonal length of A and B, and we simply calculate the Vickers micro hardness numbers, mechanical stability, low, middle, or hard.
Thank you, Professor.
Thank you, sir. Thank you.
Dear participants, 10 minutes break. Next paper presentation will start at 11:10. Mr. Dhulai Govindan will give the presentation. Thank you.
Hello. Durai Govindarajan sir, are you there?
Yes, sir. Can you hear me?
Okay, sir. Okay, sir.
Okay.
Sir, are you ready, sir? Shall we start the session?
Yeah, sure. Okay. Start. It's, I think, running out of time.
Sir, is half an hour is enough for you?
Yeah, okay, sir. Okay. I think professor is calling me now.
Just regarding that only.
Yeah, okay. No problem. I'm on the line only now.
The fourth technical session is about to begin. I request Dr. Prakash to share this session. Sir, please.
A very pleasant good morning, Anandar. Everything is theoretically impossible until it is done. Everything is theoretically impossible until it is done. Robert Hanley. I feel very proud to introduce the resource person of this session, Dr. Durai Govindarajan. Dr. Durai Govindarajan received his PhD in physics at Satyabama Institute of Science and Technology, Chennai, in 2021. And part of his PhD work was carried out in the Department of Applied Chemistry, KMU, Taiwan. Currently, he is working as a postdoctoral researcher at the Department of Chemical Engineering, Chulalongkorn University, Bangkok, Thailand, under the Professor Chiragin Pian. His research work is mainly focused on the design and development of metal oxides, nitrides, sulfides, based electrodes for energy storage and conversion applications, particularly supercapacitors. He has published 26 papers in international, well-reputed and peer-reviewed journals. He has a citation index of 735, and one of his papers is cited by 175 times. More than 4 papers have been cited with a citation index of more than 100. This shows his research qualities. Such an eminent person is among us, and he is going to deliver a talk. Over to Durai Govindarajan.
Sir, can you hear me?
Yes, sir.
Yeah, okay. Can you just wait a moment? I'll just share my screen now. Can you see my screen now?
Yes.
Can you see my screen now? Is all okay?
Yes, sir.
Yeah, okay. Thank you for the nice introduction. I think my screen and my voice is everything is okay. Then I'll try to continue my presentation. Before entering into my main title, I would like to thank the main organizers of this RTMS 2023 conference, organized by Anandar College, Madurai. And special thanks to Professor Joseph Wilson, head of the Department of Physics, and then other faculty members who are working in the same departments. Thank you once again for the great opportunity. Okay, today I'm going to talk about on the title of Advanced Electrode Materials for Supercapacitor Applications. Can you hear my voice?
Yes, sir.
Is okay, okay, okay. Sorry, because some disturbance of the network, so I cannot able to see the slides clearly. I'm sorry. If at any point you are not able to get my voice or you are not able to see my screen, you just turn on your mic and just intimate to me. It will be good for me. Okay, nice. Okay, today I'm going to talk about the title of Advanced Electrode Materials for Supercapacitor Applications. Okay. Before entering into my title, I'd like to introduce myself. I'm Dr. Durai Govindarajan, working as a postdoctoral researcher, I mean a senior researcher under the Energy Storage Research Groups, who is leading by the Professor Suradip Kivom, is the head of the department and the leader of the Energy Storage Cluster, Department of Chemical Engineering, Faculty of Engineering, Chulalongkorn University, Bangkok, Thailand. Before entering into my title, I hope my professor will explain a little bit of the university things, just bit of a slide. So here I would like to go little one by one, because this talk is mainly based on the nanomaterials and electrodes and the importance of nanomaterials, and then few things which is covered to the applications of nanomaterials. So we'll go one by one, because already you have attended good talks given by Professor Dr. Suradip and then Professor Sendil Pandian from SSN College. It was a nice talks. So we'll go by one by one. Before entering into my talk, I would like to give little things about Thailand. Thailand is a good country, surrounded by many natural resources, and it is a greenery country. And also, it's an Asian country. I hope you know and aware of all Thailand. What is that? Especially for foods and tourist destination, it's a good place. If you are getting chance, you try to come and visit here. It's nice and fantastic. And then we'll go one by one. The figure, this right hand side bottom of this figure shows the Bangkok. We are living in a Bangkok city. It's a good city, and also it's a well developed city. Hope you know that it has multiple diversities and well known cities for the tourist destination. And also here the overall the campus is on surrounded by well greenery, and then I mean lot of trees. So it's in 400 acres of the land. And this image shows the Department of Engineering, I mean the Faculty of Engineering. This whole area covers Faculty of Engineering, which is includes many departments, comes under this, like electrical engineering, environmental engineering, civil engineering, mechanical engineering. This image shows the main view of the Chulalongkorn University. It is a great university, and also which is the #1 university in Thailand for more than 14 consecutive years. And also in QS ranking, it's about around 200. I'm not sure that in 2023, but it's about 2022. It's about 200 QS world ranking. Okay, just then. Okay, this slide shows the outline of my presentation. Today, already I told you that I'm going to talk about on the nanomaterial, which is used for the supercapacitor applications. In that, before entering into our main slides, just we know our main outline of the presentation, which is includes introduction of nanoscience and technology, then classification of nanomaterials, and then synthesis of nanomaterials and characterization, and then applications of nanomaterials, and electrode material for supercapacitors. In that electrode materials aspects, I've just divided into three categories. One is metal oxide, second one is metal nitrates, and third one is metal sulfides and other electrode materials, which I'm just explaining you one by one. And finally, summary. This presentation is mainly helpful for the students who are now doing at the end of their master's degree, at the end of their bachelor's degree, because I'm not much going into the detail of my work and other things, because we try to know where the basics starting from, where the physics or chemistry or nanomaterials starting from, that you just go through one by one. In the aspect I'm just explaining you one by one. It's like a general concept. It's not in detail about subject or any mechanism or any what is that, any other things which is related to the chemistry and physics. Okay, you just try to see one by one, and then try to learn few things. At least one of our student will help from this. Okay, in the way of aspect only I'm just presenting my work here, not my work, just the general title of this presentation. Okay, we all know then, we all clearly knows that what is nanomaterial. Nanomaterial is a material which size is about, in the scale of nanometer range, which is less than 100 nanometer, we generally call it as nanometer. Okay, this is the base point of the nanomaterial. We must know what is nanomaterial. Nanomaterial, everything is made up of nanomaterials, nanotechnology, nanoscience. So we must know what is nanomaterial. As we are a physicist, so we must know the scale range. Everything is made up of nanomaterial, that few things made up of nanomaterials, not everything. In that case, the nanomaterials is a small size of material whose range is in size of less than 100 nanometers. Generally, we call it as nanomaterial. It is in, we denoted 1 nanometer is equivalent to the 10 to the power of minus 9 meter. That is called a nanometer. It is just a basic level, because many of them, I am also coming from the basic. I mean, I am also coming from the rural point of rural places. So I'm just learning. So as like one by one, which I try to learn, because this presentation is mainly for the bachelors and masters and PhD students who are at the earliest stages, not for the experts in the PhD and the experts in the academic positions or experts in the research positions. So I'm just explaining one by one. Okay, this is the nanomaterial. Nanoscience and technology are using, I mean, in the nanomaterials are using many variety of science and engineering fields, which is including in chemistry, biology, physics, and material science and engineering. In engineering, there are several aspects. For example, we are just preparing one nanomaterial. Just we are studying that nanomaterial for the application of like electronics or environmental application. That material we are just preparing and studying. Then we are moving to the device fabrication on to the next level, that we need our engineer help. So nanomaterials or nanoscience and technology is a umbrella of physics, material science, biology, and chemistry and engineering. So these are the main concepts. The nanomaterial, after discussing into the nanomaterials in the scale range, which means that 1 nanometer is a scale range of 10 to the power of minus 9 meter. The nanometer is mainly depends on the size, shape, composition, surface charge, and agglomeration. As we know that clearly, nanomaterials or nanometer is very, very, very less. We cannot see in our naked eye. That we can go to the, just move to the next slide to see what are the things are there, whether we can see or not in our naked eyes in the nanomaterials. Okay, this is a very good slide. In this, we can see. Hope you will all understood what I have mentioned it. You see, people can see at certain ranges in the scale range. You take a scale, it is about small scale level, it's 0 to 15 centimeter. On the bigger scale, it's 0 to 30 centimeter. We can see easily. What you will do for the nanometer scale range, that will mainly covers by the physics, I mean the physicist. What it means, you can see I mean, you can see the human being or else a tree or as a big things in your naked eyes. If you go to the lower level of that in the scale range, you cannot, you can see, but you cannot see like as a larger. You see here in the meter scale range, there are human beings are there. We can see at most a few meters. And then you just forward to the millimeter, as a physicist, that you can see 10 to the power of 3 minus 3 range, that we can see B as a small What living things we can see as a millimeter level. Then you go for the white and red blood cells in our human body that we cannot see. In that cases of microns and what is that, 10 power 3, 10 power minus 3, 10 power minus 6, 10 power minus 9. What is that? 10 power minus 3 means millimeter, 10 power minus 6 means is a micrometer or micron, or 10 power minus 9 means micrometer. You can see up to the level of 10 power minus 3 in the aspect of a small insect. Then you can go for the human blood cells, which is in the range of micrometer scale range. We cannot see in our naked eyes. Then you go for the nanometer levels. It's totally, I mean, we cannot see, absolutely we cannot see. Okay, in that scale there are so many materials, so many things are there that we can see one by one. Okay, here in previous slide we have just remember that we just seen what is nanomaterial and what about the scale range of that nanomaterial and what are the things involved, I mean in the physics concept involved in the nanometer, things to explain one by one. Here classification of nanomaterials. Then nanomaterials can be classified into many things, like it is based on the shape, it based on the phase composition, it based on the structure, it based on the material, it is based on the origin and sources, it based on the crystallinity. For example, there are 5 persons standing in front of us. We cannot say who is tall. Without seeing him, we cannot say that who is tall, who is fatty, who is lean, who is white, who is black, like that. Okay, without seeing. If we see, we can classify them as who is female, who is male, and then who is fatty, who is lean, like that. As wise, we can classify the nanomaterials into many things, like shape means what is this? 0 dimensional, 1 dimensional, 2 dimensional. You are a physicist, if you are all aware of that, what is 1 dimensional and what is 0 dimensional and what is 2 dimensional. Again, I'll just try to explain. 0 dimensional means it's like a quantum dots. It is very, very, very small things that we can say it is in quantum dots. And then 1 dimensional means it has some nanometer scale range in the nanometer level. So it's like it means it consists of nano tubes, nanofibers, nanowires is called as a 1 dimensional nanomaterial. And then the second thing is nanofilm, nanodisk, and nano layers. What at all those things? Anything can be coated over the surface. For example, you are taking a glass, or you just see in our wall, you are just painting, just you are coating a material over your wall. That is also a nano material. You just go through what are the nanomaterials are using, but we are blindly doing just buying, painting and coating on what are the nanomaterials are involving in those paintings, that you must know, because everything is made up of, most of the things nowadays made up of nanomaterials and nanotechnologies. This point and this word is very, very, very important. Okay, and then other aspect, phase composition. Once you know about the shape and dimensionality, then you go for whether it is single phase or whether it is a multi-phase with different structure, that you must know, because in periodic table there are several elements are there with there are like several metallics and metals and non-metals, and like so there are so many metals are there in our periodic tables. From that only we are going to explain one by one. Phase composition also important. Nature of the material. Nature of the materials means in the case of the pure materials, or it should be in metal oxides or sulfides or nitrites or carbides, everything that I have listed here, few material which is based on the metal oxide. I think you will be confused here, because there is an image. What is that? There are many things are covering with this. Everything has their advantages and disadvantages. In that case, I am explaining you one by one from the base level. Okay, that's why I'm going slowly. Okay, then once you try to know the dimensionality and composition and structure and nature of the material, you just go for the origin and source. Origin and source means for example, some materials we can get easily. You see some what is that, sodium chloride crystal is easily available, that we can see in the sea area, that is NaCl and also some main of the metals which is available, like iron based, manganese based, lithium based, everything we can get as a normal, I think, like abundant. And some materials cannot be get, but we have to fabricate, we have to synthesis, we have to develop. Okay, in that cases there are two types. One is easily available and non easily available, I mean natural, and then we are engineers, engineers and scientists just making the nanoparticle, just making the nanoparticle. Then you have to understand what is crystallinity. There are 7 crystal systems are there, that you know what is FCC, what is BCC, what is hexagonal, what is tetragonal, what is cubic. You just try to know, just open your mind and just catch some points. Okay. Okay, everything is made up of I mean, in the case of nanomaterials, everything is made up of these 3 things. One is crystalline, second one is polycrystalline, and third one is amorphous. What is crystalline? Crystalline means the atoms are arranged in regularly or arranged in a particular manner, that is called crystalline material. Okay, if you see a crystal lattice, for example zinc oxide or I mean titanium dioxide, you can see the number of atoms, or the atoms are arranged in a good manner, at a correct manner, at a correct orientation. That is called as a crystalline material. Polycrystalline means a group of atoms in the same material arranged in a particular orientation. For example, here you can see these all one group. Here you can see one group is made up of one orientation. The second group is made up of different orientation. That is called polycrystalline. The word is poly and then linked with the crystalline, which means that the crystalline materials are, I mean, the orientation of the crystalline materials are arranged in different groups in a compact boundaries, I mean grand boundaries. And then amorphous means the atoms are arranged in irregular manners, like sitting the atoms are here and there in a material. That is called amorphous. For example, there are so many materials like glass, we cannot see atoms. I mean, the most of the non-conductive materials are the amorphous material, like glass, some wooden, some fiber. These things are the amorphous, which is based on the atoms arrangements. Okay, I hope you understood from this slide. Then we move on to the next slide, which is synthesis of nanomaterials and characterization. Okay, I just remember this presentation is mainly for the students, not for the experts. I am sorry, not for the experts. Anyway, at least one of our student would be helpful from these slides or this presentation. That's my point, because I am not go into the depth level of my work and then publications and then direct to the application level. Okay. As I said, this slide shows the synthesis of nanomaterials and nanoparticles and its characterization. You see, nanomaterials, simple thing. Nanomaterials can be prepared using 2 types. One is bottom-up approach and another one is top-down approach. In bottom-up approach, we are just taking some chemical precaution, just mixed it together, and we are getting some nanoparticles. Okay, I mean, molecules, ions or atoms chemically involving or chemically doing some reactions and giving some nanoparticles. In the aspect of top down approach, it's a purely mechanical and physical concepts based nanomaterial synthesis techniques. What in the bottom up approach, it's purely chemical synthesis based. What is that? We are taking some, as I said, we are taking some chemical precursors, just preparing some materials based on that chemical precursors, whether it may be, for example, you are going to prepare some zinc oxide. You need to take zinc nitrate or zinc acetate or some reducing agent or some other agents. Based on that, you are getting some nanoparticles, like chemical reactions involving air. In the aspect of top-down approach, we are just peeling off, we are taking off, not by manually, by giving some current or giving some extra power. We are taking some material from the solid to the nanometer level. I mean, hope you are all know or doesn't know means no problem. Sputtering technique. It's a well-known physical vapor deposition technique, which is used to fabricate a very good thin film which high crystallinity with uniform and high adhesion coatings. Okay, in that case, that is a top-down approaches. Okay, what is happening in top-down approaches? We are just giving some power to the target material, which means the main source material, that the atoms are ejected from the main target material, and it is interacting with some oxygen or nitrogen or some other reacting gases. It's forming as a M and O2, which M is a metal or O is means oxides, just forming like some MO2 oxides. I mean, it's like metal oxides or metal nitrates. Then once you prepare the nanoparticle, you just need to study in the aspect to know what are the important physicochemical characterization and electrical characterization or optical characterization or mechanical characterization. Like there are so many techniques are there. In that case, I have just mentioned here SEM, scanning electron microscopy, TEM, transmission electron microscopy, AFM, and UV, and what is that, FTIR. Each and every technology or each and every characterization tool having lot of advantages. From that we can get many things. For example, FTIR, we can get the compositional analysis. You are just preparing zinc oxide or titanium dioxide or copper oxide, nickel oxide. What are the composition, how they are how they are connecting, how at which region we are forming, and which temperature, and is whether it's forming the certain metal oxides or not, that we can find it from the FTIR. And the main thing is the X-ray diffraction analysis. This is one of the important analysis. Okay, based on the Bragg equation. Hope you know or just heard about this Bragg's equation and crystallite and what crystallinity, those things from what is that, from your physics master's second year or first year students. I just remembering these things. Everything is I just deviated from this thing. Okay, once you prepare the nanomaterial, you just go for the basic characterization of X-ray diffraction analysis to study their structural and crystallinity phase of their material. And then if you go for X-ray photoelectron spectroscopy, you can find out the binding energies, which is related to the surface chemistry of the material, where and I mean how it's binding, which orbital, which position, which states, that you try to know from the XPS analysis. And then TEM, it's a very beautiful technology. From TEM you can get in depth like a 5 nanometer scale range of our material properties with selected area diffraction, how the ring patterns are arranged, whether it is crystallinity or not, which orientation it may be, like Miller indices, like HKL plant. There are few HKL plants are there. It depends on the material. Likewise, we are investigated their material properties. I mean, the nanomaterial properties using various microstructural and optical electrochemical properties. Okay, in the aspect of electrochemical energy storage devices, that I'll explain you in the slides which is coming next. Like, okay, once you confirmed that material where we are going to adapt, or where you are going to use that material. For example, you're using some metal oxides, which will be good for optoelectronic properties. You're preparing some nanomaterial, it will be good for sensor applications. You are preparing some metal oxides or nitrates or sulfates, will be good for the supercapacitor or battery applications. You are preparing some nanomaterials, that will be good for the antimicrobial or cancer applications. Like, once you confirmed, you just must know the properties of that materials. You just adapt those materials to the different application aspects. Okay, that's why I'm explaining you one by one. Okay, then these are the general slides. I'm sorry, these are the general slides. Once you prepared and studied their properties, then you just take into to the next level of their materials to the application wise. Nanomaterials, you know that in our day-to-day life you are using in variety of applications, even in optical engineering, nano electronic devices, nano biotechnology, medicines, energy, defense, ceramics, nano fabrics, and cosmetics. Like everything is made up of nano. Most of the things is made up of nano material. That's why the nano material, each and every metal has a beauty and their good advantages. I mean, the better advantages for the different application that we are going to see one by one shortly. You see, in nano electronics, you know very well. In nano electronics, you heard about that the smart TV and smartphones. Recently, Samsung has launched what is that, flip flop phones. It's high end model of flip flop phones. You can just open and close without any damaging of your phone. And then some coatings over the phone, and the smart watches, Apple watches, or some Redmi watches. These are the things which you are using in our daily routines. I mean, this is nowadays it's must like the things. Okay, in that cases, for flat panel displays, some coatings, some metal oxide based coatings have been coated over this glass. Then it will be good for the visibility and then the flexibility and transparent nature. Likewise, not only in that cases, nano transistors, sensors, and then it can be, nanomaterials can be easily absorb energy within few seconds from the help of battery. I mean, the electrical conductivity is much higher. And also the main thing, the weight and thickness is very important thing. You cannot for example, you can see a smart watch or inbuilt with smart watch with sensors. If it is in 5 kg, you cannot carry or you cannot wear and hold every day. Even if you wear the smartwatch, it's very small thing. Okay, it's like in grams. Even it's like in grams. This made up of the coating is made up of like TiO2 or some nitrate, gallium nitrate coating. There are so many coatings involving in these to make affordable and flexible and many applications in nano electronics. And the second thing, nanomedicine. Now, in the aspect of nanomedicine, you just consider and just think about gold that just wearing our as a chain or ring or whatever it may be the thing. As our what is the daily habit, that's common thing, like I don't know how to say. Okay, anyway, few nanomaterials which are from the based on metal or gold, silver, silica nanoparticles are mainly used to treat for the cancer therapy. And also some of the nanomaterials will be used to stem cell differentiation and the artificial DNA production. Then some of the nanoparticle can be used in the chemography, which means that some drug type of treatment, which means drug treatment that uses using I mean, the based on the some powerful non-toxic chemicals to kill the unwanted cells in our body, whether it may be a cancer cell or other cells. Okay, recently some research is going on to development of the vaccine for the virus cells. Okay, hope you know we affected a lot for this COVID situation. There are so many groups are working to find the good material for the vaccine production. And then one more thing, in the base of carbon material, the single layer of atomic graphene is mainly used for the cancer treatment, which means the computer contact lens due to the transparency and wound healing. Wound healing. So in nanomaterials, there are many applications. I mean, the few nanomaterials are mainly used for the nanomedicines also. And then these are the things we are going to explain in the aspect of cosmetics. in our day-to-day life, we are going to use some facial creams and some what is it, some coatings in our face. Like there are many. I cannot able to remember that names. Like facial creams or sunscreens and body lotions. Everything is made up of nano materials. You see the beauty of titanium. The beauty of
Sir, Durai sir,
yeah, please.
due to time constraint, could you finish your talk within 5 minutes, sir? Is it possible?
Yeah, sure. Okay.
Thank you, sir.
Okay, okay, it's okay. Nanomaterials can be used in cosmetics also. These are some nanomaterials which is based on titanium dioxide and zinc oxide. Then just we are moving to the next. And also nanomaterials can be used as a fertilizer to test the soil property to grow the crops in agriculture fields also. And then the same. Okay, we are directly moving to the energy field. Apart from those agricultural, medicine, and cosmetics and other things, we are moving into the next level, which is energy. Energy is very, very important. Without energy, we cannot do anything. Even human being, we need energy for that. Supplement. We are taking some food and some supplementary thing. Likewise, electronic gadgets or things also can be needed some energy. In the aspect, we are going to focus on the energy storage devices. There are many energy storage devices are there. In that cases, I am going to explain few things about supercapacitor. In supercapacitor, based on the energy storage mechanism, I mean electrostatically, which means carbon based materials are the electrostatically energy storage devices. That is the EDLC type capacitor. And second one is the pseudo capacitor, which is the charge can be stored electrostatically. I mean the Faraday reaction involving in the electrode and the electrolytes. Based on these things, we are just explaining the concept of mechanism of the energy storage mechanism in the field of supercapacitors. Okay. Then the development history and advances in supercapacitors. You just know in the early 50s, in 1950s, we just started the supercapacitor research, which is using the carbon-based materials. Like there are two electrodes separated by an insulating layer. Two electrode is based upon the carbon materials, as I said, in which store charge electrostatically. Then moving into the next level in 1970s, researchers have been focused to the other class of metal oxides or metal hydroxides or sulfides and conducting polymers. In the combination of these two, I mean the EDLC and pseudo capacitor, researchers have been focused to the hybrid or asymmetric supercapacitors in the early 90s. At present, we are at the stage of developing stage of the micro supercapacitor, wearable capacitor, cell powered one, and transport which can be usable for the transport properties and portable devices. Like how the supercapacitors from the 1950s, how it reached to the 2022 centuries. I mean in the development in the aspect of applications. Okay. Then sorry, just I'll explain you one by one in short manner because of time constraint. Okay. You see there are several class of materials can be used for the electrochemical energy storage devices, particularly supercapacitor, whether it may be a metal oxides, whether it may be a metal nitrates, or whether it may be nitrites or sulfides or phosphides and carbides. There are several materials are there. The beauty of the thing is each and every material are their advantages and disadvantages. You see in the aspect of metal oxide, it has low cost. The most of the metal oxides having low cost with excellent redox activity, with low molecular weight and structural stability and porous structure. Okay, as I said that ruthenium oxide is one of the most advanced, not advanced, which is the base of the pseudo capacitive electrode materials. Why? It means because of these properties, it has the valency states, good conductor, and good electrochemical stability. These are the main advantages. In the aspect of supercapacitor, there is a current collector. Any current collector means any conducting substrate or foil can be used as a current collector. Over the current collector, we are just coating some metal oxides or some other compounds. You see, there what is the electrolyte ions interacting with this material and then getting some charge over the current collector. Okay. Few of researchers, I'm just going to display here. You see, up to now at this 2023, there are so many metal oxide based electrodes have been characterized and adopted for the supercapacitor application. You see, this is the metal oxide and this is carbon based electrode. Combination of this, we can get the I specific capacitance more than 200 farad per gram. Like these are the main metal oxides which is based on the which is used for the supercapacitor application. Why metal nitride? It has a multiple oxidation states. It should be high theoretical conductivity. It should be stable. It should be chemically inert. These are the main advantages. These are the advantage properties of these metal oxides. Then we just move on to the some work which is cobalt oxide based supercapacitors is prepared by hydrothermal synthesis. You see the beauty of nano wire or nano some like our air type structure. It will reaching the maximum capacity, and also you just go for these other metals of manganese oxide and iron oxide composites and manganese oxide bowl. Why I am explaining you these one by one means everything is made up of nanostructure with different structures, with the different sizes, with different phase. So every metal oxides cannot be adapted for supercapacitors because it has different structures and stability and multiple oxidation states, which will be beneficial for the high performance supercapacitor. Then move on to the next metal oxide. Metal oxides also the high class of electrode materials for the fabrication of supercapacitors. Here we are prepared manganese oxide based electrodes using magnetron sputtering technique. Here we have achieved the aerial capacitance of around 100 millifarad per centimeter square using 1 molar KOH electrolyte. Not only KOH electrolyte, we are studied their electrochemical performance in 3 different electrolytes. As I said, one is KOH and another one is potassium chloride and sodium sulfate. Here KOH is the excellent showing the excellent electrochemical performances because of their ionic radii and hydrated ionic radii of the K and OH minus is K plus and OH minus is very less compared with these 3. And then some of the work has been fabricated using some other metal nitride. You see, this is a small device can generate more energy, which is based on the nitride, which is based on the vanadium nitride film, showing the maximum capacitances. Then other class of materials are the metal sulfides. There are so many metal sulfides. You see one by one. Yeah, please, just 2 minutes.
Sir. Yes, sir.
Then recently researchers have been focusing material which is made up of the 2 metals with some other compound which is like Ti3C TX and other metal selenides and phosphides and phosphates. Okay, these are the upcoming and booming materials for the energy storage applications. Okay, as I said, nanomaterials in the aspect of energy field, we can use many things like engine startup for the electric vehicles or some solar panels. It's just connected with solar panels to store the power from the solar panels. Likewise, there are so many applications in our day-to-day life. Okay, then summary, just we have discussed as a general concept of the importance of nanosensor technology, how it's impacted to our day-to-day life. Then the synthesis of nanomaterials and its characterization were clearly discussed. And then the applications of nanomaterials in the aspect of medicine, electronics, energy, using various oxides and nitrides electrode materials. Thank you for your kind attention. I'm sorry for the delay. Thank you. Thank you.
Thank you, sir. You have covered from the bottom to the top as per nanotechnology word. Participants, if you have any doubt, you can ask. Otherwise, post it in chat box.
Yeah. I just covered just few percentage, not all. If you have any doubts, you please mail me. Just don't it down my email ID. Or if you are having interest to visit my lab, or if you are interested to apply for internships or PhDs, those who are working, those who are doing masters from chemical engineering or chemistry, who is working for the electrochemical energy storage, you try to contact with me. I'll try to help you for PhD or internship or collaborations. Just note it down my email ID and contact me.
Thank you, sir. Thank you for your wonderful presentation.
Thank you, sir. Thank you for the great opportunity. Again, I'd like to thank Professor Wilson, sir, for the chance. Thank you. Thank you for the other organizers also. Thank you.
Thank you, sir, for your informative talk. The fifth technical session is about to begin. I request Professor B. Bhuneshwari to chair the session.
Good afternoon, everyone gathered in RTMS 2023, both virtually and in person. Nano, thinking small to think big. Here comes an eminent personality who has a wide strength in thinking about this small entity, definitely will take us to travel a long journey in this mysterious nano world. Yes, it's my privilege to introduce the research author of Technical Research 5, Dr. M. Victor Anthony Rhodes, Assistant Professor, Department of Physics, Loyola College, Chennai. Dr. M. Victor Anthony Rhodes brought up with sheer vision, completed his BSc Physics in the University of Madras, Chennai, MSc Physics in Bharathidasan University, Trichy, MPhil Physics in Arul University, Melbourne, and finally came out with flying colors by pursuing his doctorate degree from the University of Madras, Chennai. He has 20 years of experience in his teaching career. I feel proud to say that he received the prestigious award, Reverend Dr. NFLE Research Award for the academic year 2018 to 19 and also 2019-20, which is given to Loyola College faculty members for publishing maximum number of research manuscripts in an academic year. He was the guest editor of Materials Today Proceeding of ICME 2018 One Day Part 1. He organized nearly 5 conferences on material science and materials for energy and environment. He gave invited talks in many national, international centers, conferences, workshops, and various fields. He has 11 years of research experience. Under his guidance, 5 students pursued PhD, 4 are pursuing PhD, 3 completed F1, and he guided 70 MSc student projects. He acted as the journal reviewer in many reputed journals like Journal of Materials, Journal of Physics and Chemistry, Materials Letter, New Journal of Chemistry, Solid State Sciences, Nature Scientific Reports, International Journal of Energy Research. He published 63 research papers in reputed international journals. He also presented 50 research papers in many national and international conferences. He is remarkably known not only for his academic excellences but also for his active role in various extension activities. He acted as the NSS program officer in Loyola College. He acted as youth Red Cross coordinator. He acted as the Loyola Physics Association president from year 2016 to 18, and he is a member in Loyola Institute of Practical Energy. He was the vice president of Loyola College Physics Staff Association from the year 2018 to 2020. He acted acted as the health and wellness club coordinator in Royal College. In addition to all the institutional activities, I came to know about him from the convener of RTMS 2023, that Dr. M. Victor Anthony Ross is social activist. He is a man with pure determination and confidence who explores the world in his own style and service as a greater ladder in lifting up many students. Hence, I pray that his contribution to society may still continue and his teaching career became a grand success. It is indeed an honor to invite Dr. M. Victor Anthony Rose, resource person of this magnificent fight, for delivering his talk on nanocoating society for integrated energy system. Please, sir.
Thank you, ma'am. Am I audible, ma'am?
Yes, yes.
Yes, sir.
Thank you, sir. Thank you, ma'am, for your nice words of introduction. I'm happy and privileged to attend this international conference. First, I thank the organizers for giving me this opportunity, especially Dr. C.S.A. Raj, my close friend when he was working in Viola College. We used to talk a lot about material science and other things. Thank you, sir, for giving me this opportunity. I will straight away go to my session. I'll share my screen. Is my PPT visible, sir?
Yes, sir. Your screen is visible.
Thank you, sir. So my topic of discussion now is nanocomposites for integrated energy system. Under my guidance, 4 PhD students are working. We are all working on nanomaterials to integrated energy system. Integrated energy system in the sense we are trying to join solar cell and supercapacitor. Already this field is emerging. Only few have worked in this field. Uh, Along with that few, we are also working on that. We have researched many nanocomposites for solar cells as well as for supercapacitors. For solar cells, photoanode material and the replacement for counter electrodes. In supercapacitors, that working electrode. For all these things, our nanocomposites will be useful. My order of presentation will be introduction about the photo supercapacitor, energy need of the world, and introduction about the photo supercapacitor, components of photo supercapacitor, solar cells. It is one of the component of photo supercapacitor. As I told, we are trying to integrate the solar cell and supercapacitor in a single device. That's our area of research. So in solar cell, which part of solar cell, which type of solar cell shall be taken and integrated? I'll explain that. And supercapacitor, my previous speaker has spoken a lot about supercapacitor. I will also talk few things about the supercapacitor and summary of the discussion. So this will be my order of presentation. First, introduction. We are all living in an energy deficient world. Our energy need is enormous, especially clean and green energy is the need of the hour. Without this clean and green energy, we are living, what to say that, a carbonized world. That carbonized world gives lots of pollution to the environment. Inhaling those polluted air causes many diseases in the human being. One of the main example we witnessed in our life, COVID-19. It's due to the inhaling of the carbonized air. Affection of our lung is affected, so that we are all, the whole world is affected by that COVID. Why? Because of the defect lung the human being are living with. The reason for the defect lung is carbonized air. That carbonized air is due to the excess polluted power consumption. So decarbonizing the power sector is a fundamental step to reduce emission. especially in an increasingly electrified world. For that, we have to deploy many number of renewable sources. So the deployment of renewable power is one of the main enabler of keeping the rise in average global temperature below 1.5 degrees Celsius. If we didn't employ or deploy renewable sources, what will happen is our global temperature will keep on increase. We will inhale lots of carbonized air, so our lung will be affected more. So we will not live a healthy life, and our future generation will also lead unhealthy life. Recent progresses has been promising. Initial estimates suggest that 2022 is a record year for renewable capacity addition with an annual capacity of just a minute, 340 gigawatt of renewable energy power addition is taking place in the globe. Next, in 2021 alone, renewable electricity generation rose by almost 7%, a record of 522 terawatt hour increase, with wind and solar photovoltaic technologies together accounting for almost 90% of this growth. If this growth proceeds in this way, surely we will achieve that zero emission which that International Energy Agency has envisioned. In 2050, the globe will witness a zero emission. The globe will be a zero emission globe. So we all pollution free power sources like that. Uh, Envision is there. Thought is there with us, with the most of the world. So that will be achieved if we grow like this. The share of renewable energies in global electricity generation reached 28.7% in 2021 after a modest growth of 0.4 percent points. So it need to be increased every year. A lot of renewable energy sources should be installed, commissioned, and the whole world should use a renewable energy source alone. Then we will lead a pollution-free life, and the environment will be pollution-free. In India, coming to India, those are all the things about the world. Coming to India, solar capacity increased in the last 7.5 years from around 2.6 gigawatt to more than 46 gigawatts. Renewable energy has a share of 26.53% in India in the total installed generation capacity in the country. So India is the world's largest renewable energy expansion program. It possesses the fourth global position for overall installed renewable energy capacity, with an installed capacity of 175 gigawatt till 2022. So India is marching forward with the renewable energy sources. Many electric cars have come in the roads. These are all significant improvement in human life. To consume the electric car, to use that electric car, we should not rely on the carbonized power source. Instead, we should rely on the renewable energy source. That is one of the idea behind this photo supercapacitor, which integrates the solar cell and the supercapacitor. Then in India, solar capacity increasing in the last 5 years the same way. So this globe could be left pollution free to the future generation if we explore and adapt a new system that integrates solar energy harnesses and storage in a single device called photo supercapacitor. This is the schematic diagram of photo supercapacitor we ideated. In this photo supercapacitor, you can see the top one is the conducting glass, then at the bottom is again conducting glass. Above that conducting glass, that collector electrode is coated. Then non-redox electrolyte is inserted above the collector electrode. Then intermediate electrode is there. Redox electrolyte is there. Photoanode is there. Conducting glass. So this is the integrated structure of photo supercapacitor we ideated. This integrated structure of photo supercapacitor can be dissected and viewed like solar cell part, and supercapacitor part. In solar cell part, as you all know, a conventional counter electrode, redox electrolyte, dye incorporated photoanode, FTO glass. In our laboratory, we are trying to integrate the dye sensitized solar cell and the supercapacitor, so that here we got that redox electrolyte and dye incorporated photoanode part in solar cell part. In supercapacitor part, as you all know, learned from the previous speaker, collector electrolyte, collector electrode, non-redox electrolyte, working electrode, the supercapacitor part. So the overall photon to electron conversion and storage efficiency of this photo supercapacitor is calculated as a ratio between the efficiency of electric double layer supercapacitor and the efficiency of the solar cell. So of CV square by power input, and this TCH is the time of charge needed to arrive at the final potential of the electric double layer capacitor, and the dynamic surface area of the dye sensitized solar cell. This is the final mathematical expression used to calculate the overall efficiency of the photon to electron conversion and storage efficiency of the photo supercapacitor we proposed. If this efficiency is very high, then our photo supercapacitor will come into market, will replace the existing battery system in the automobiles. Existing battery system in automobiles works on rechargeable batteries. If our device, photo supercapacitor, comes to the market, is successfully passes all the test, then you can think about solar operated car in common. So the components of photo supercapacitor comprises two parts as is shown in the schematic diagram, solar cell sector and the supercapacitor sector. Here we are using dye sensitized solar cell. Other types of solar cells can also be used. You people can think about the usage of other types of solar cell in the photo supercapacitor. And this dice in our laboratory, we are, as I told, we are using only this dye sensitized solar cell. It has a dye incorporated semiconductor photoanode. The dye incorporated semiconductor photoanode is deposited on a conducting glass substrate, redox electrolyte and counter electrode. Then the supercapacitor can be either pseudo type supercapacitor or EDLC or a hybrid supercapacitor. Either any type of supercapacitor can be used in the integrated device. Now coming to the active materials of this photo supercapacitor, photoanode, which is a part of the dye sensitized solar. Mostly, as you all know, metal oxides are the frequently admitted materials that could be employed as a photoelectrodes. But practically, those metal oxides are practical in the sense in the market, those metal oxides didn't come as what to say that material in commercial solar cell. Still, commercial solar cell uses silicons. Metal oxides may come in future if the research continues in the same phase, and we will get that. The deciding parameter of a good photoelectrode to boost the photo conversion efficiency, surface area, morphology, purity, high transparency, low light scattering property, and mobility of the metal oxide particles. The available surface has a beneficial effect in deciding the quality of the photoanode. So surface morphology is very important in making the metal oxide as a photoanode. So the smaller the particle size, the larger the surface area, and vice versa. So nanomaterials could be the actual source in as photoanode in the solar cell. These are all the various materials researched and reported for photoanode. Here you could see that titanium dioxide doped with cadmium gave an efficiency, photo conversion efficiency of 13.2%, 13.29% with an open circuit voltage of 0.8 volt. So this titanium dioxide doped with cadmium oxide is synthesized using hydrothermal method. That's the maximum efficient material reported here. So you can think about this material. You can think about other equivalent material which will act as a photoanode in that thing. Then dyes are the next important parts in the dye sensitized solar cell. This dye sensitizer is a significant piece of the dye sensitized solar cell because it assumes an imperative, very important part in absorbing the irradiate light and channelizing the photo-generated electrons to the conduction band. The dye must be checked in the following aspect to qualify as a suitable one. It should cover a wide range of frequencies, including visible, infrared, even ultralight. So in all these ranges, that dye should be. Then this dye allow the acceptance of electrons, that is HOMO, mistakenly it is right. HOMO of the dye must lie lower than the thing. Then reducing the energy loss in the process of transferring the electrons, the dye should have a narrow band gap between the LUMO and the conduction band. The dye should have adhering ability to stick to the surface of the photoanode. So these are all some of the properties a dye should have to be used as a dye in the photo supercapacitor. Photo supercapacitor as dye in the dye sensitized solar cell. These are all the various dyes researched and reported in the literature available. Here you could see the open circuit, maximum open circuit voltage is given as 0.612 volt is the maximum open circuit voltage, and the efficiency is 2.09. So this phytoameriana fruit, beta natural dye, pigment is beta alanine. So you can think about different dye like this, and you can do like that. So far I have told you about photoanode, dye. The next part is electrolyte, which is a fundamental part in the dye sensitized solar cell, which serves as an arbiter between the counter electrode and the dye in dye regeneration. Because in dye sensitized solar cell, once the dye is used, then it will die. So it should not happen. It should be regenerated. So an electrolyte should contain the properties of high electrical conductivity, low viscosity for electrical diffusion, desorption, free from dye. So these are all some of the properties of the electrolyte. So that electrolyte can be used in the dye sensitized solar cell. There are three sorts of electrolytes, in particular liquid electrolyte, solid electrolyte, and quasi-solid state electrolyte. Liquid electrolyte, solid state electrolyte, and quasi-solid state electrolyte. The very basic for the liquid electrolyte used in dye sensitized solar cell photo supercapacitor is iodine ions. The major drawback in using liquid electrolyte is that they leak and are dangerous due to the presence of toxic thing in that liquid electrolyte. To fix this leakage issue faced by the researchers, people have developed solid state electrolytes made up of a semiconductor. The semiconductor should be a p-type material, so it can act as a hole transfer material. The selected hole transfer materials are usually copper-based one. So copper iodine, copper bromide, copper, all these things can be used as a solid electrolyte. The next type of electrolyte is quasi-solid state electrolyte. The quasi-solid state electrolyte is formed by the mix of the fluid and solid state electrolyte. Gel type can be used as quasi-solid state electrolyte. So like that, three types of electrolytes can be used in the dye sensitized solar cell to improve the efficiency of the dye sensitized solar cells. These are all various electrolytes research. So here you can see that the photo conversion efficiency is maximum for this liquid electrolyte. The electrolyte is iodide I3. So these are all the things. The next part in the dye sensitized solar cell is counter electrode, which converts the iodide ions to triodide ions through reduction, thereby regenerating the dye molecules. So the counter electrode should act as a catalyst and enhances the reduction rate. Photovoltaic part directly depends upon the catalytic activity of the counter electrode. Counter electrode is also an important part in the dye sensitized solar cell. The contrast between the Fermi level of the semiconductor and the redox potential comprises the open circuit voltage, which is marked as zero current. These are all various counter electrodes researched and reported. So here you could see the maximum efficiency is given by this glycol treated pedot as counter electrode. So other counter electrodes are reported there. Other color counter electrodes are reported there. So these are all the active parts of the solar cells in supercapacitor, photo supercapacitors. Next to photo supercapacitor, you all know how a supercapacitor works. It stores 100 times more energy. It has high energy density, high power density, high capacitance,
Excuse
long
me,
life.
sir, sorry for the interruption.
Yes, ma'am.
Sir, could you please finish your presentation within
Yes,
5 minutes?
sure, ma'am.
Thank you.
Thank you. So this is the principle and construction and working of the photo capacitor. These are all the important points about capacitor versus batteries. These are all the types of supercapacitors. So in this types of supercapacitors, these are all the electrode materials of pseudo type supercapacitor. Here the power density is maximum for this zinc oxide, nickel oxide, copper oxide nanocomposite. This is the power density. Well, the only drawback in supercapacitor is energy density will be very poor. So the high energy density is the need of our for that. Then this is the various electrode materials reported for electric double layer supercapacitor. In this, the power density is maximum for this reduced graphene oxide and that NPC hydrogel electrode. Then these are all hybrid supercapacitor reported, electrode materials reported hybrid supercapacitors. So here you can see all the high power density and energy density. Then electric double layer, double electrode photo supercapacitors. So here this counter electrode converts the iodine ions to triiodine ions to reduction, thereby regenerating the dye molecules. This is the schematic structure of the double electrode dye-sensitized photo supercapacitor. Here you could see a separator between the solar cell and the supercapacitor. So charging electron, and here also the charging electron. This is the 3 electrode dye sensitized photo supercapacitor, dye sensitized to solar cell photo supercapacitor. These are all schematic structures. So you researchers can increase or improve the schematic structure and bring a device this. So these are all the publications we did in the last 3 years based on the nanocomposites, MnO2, copper oxide, reduced graphene oxide. Then based on pH, how the supercapacitive behavior varies. Based on temperature, how the supercapacitor varies. All these things we researched and reported. Participants can go through these papers and know more about the things. And this is our recently published paper, a quaternary nanocomposite. So we are researching binary, ternary, and quaternary for as a counter electrode for dye sensitized to solar cells. This is our another paper which is reported in Journal of Electrochemical Society. Here we reported 2 different morphologies of nanocomposite, rod morphology and sphere morphology of MnO2 in the ternary nanocomposite. So people can go through this paper and learn more about our materials, nanomaterials for integrated energy system. Thank you. Thanks for the opportunity, sir and madam. Thank you. If you have any questions, you can ask.
Thank you, sir, for your nice presentation. Dear participants, if you have any queries, you can ask. A resource person is ready to give his answer. You can also post your queries in the chat box. Sir, I have a question, sir.
Yes, ma'am. Yes, ma'am.
See, in one of your slides, you mentioned the dye should be hydrophobic. Why it shows? Sir, you're not audible.
Water will interact with the dye, ma'am. Chemical reaction will take place. So the property of the dye.
In case of the organic dyes, natural dyes.
Natural dyes, yeah, it should be sealed from the environment so that it is stacked between the photoanode and the thing. So only light interacts with the dye, and it boosts the efficiency of the ejection of electron from the photoanode. That's the purpose of this dye sensitized solar cell. Dye in the dye sensitized solar cell.
Okay, sir. Thank you.
Now the sixth technical session is about to begin. I request Dr. Sophia to chair the session. Ma'am, please.
Dr. Bhagyaraj, are you there? Are you available?
Good afternoon, everyone. We are happy to have our invited speaker, Dr. Bhagyaraj Perumal, in midst of us. Currently, Sar is working as a Helen Giller Quantum Research Fellow in Sarah and Moshe Jezebel Nano Electronics Center, Technion, Israel Institute of Technology, Israel. I'm very happy to register here that Dr. Bhagyaraj Perumal did his UG Physics degree in our Anandar College, and I'm happy to say that he is my classmate and good friend of mine. He did his MSc in Lyra College and got MPhil degree from Pondicherry Central University. He completed his doctorate from National Taiwan University, Taiwan. He is a man who has received many fellowship honors and awards at such an young age. He is a topper and gold medalist in both his UG and PG degrees. He was awarded Young Scientist Research Fellowship by Atomic Energy, Government of India. He also received Summer Research Fellowship from Indian Academy of Sciences, Bangalore. Department of Information Technology, Government of India, awarded him National Photonics Research Fellowship. Taiwan International Graduate Program Research Fellowship was awarded to him by Taiwan International Graduate Program. Still, there are many more honors and fellowships to add to his credit. He is currently under Helen Giller Quantum Research Fellowship from Israel Institute of Technology. His major research thrust areas are two-dimensional semiconductors, organic, inorganic, perovskite semiconductors, high-performance devices such as photodetectors, LEDs, lasers, etc., 2D heterostructures, and flexible electronics. We are happy to have a session with such an eminent personality. We welcome you, sir, to share your expertise with us. Thank you.
Sir, audio not able.
So can you see my screen? So, hello?
Oh, yes, sir. Yes, sir.
Yeah, okay. So thanks for your introductions. So I can start my talk. So today I'm going to give my talk on optoelectronic device fabrication based on 2D semiconductors. So this is my outline of talk. So the first I will introduce the basic concept of 2D semiconductors. Then I will go into the experimental sections. In these sections, I will discuss about crystal growth and the device fabrications. So the following session will be the device performance. So I will explain one by one. So the finally it will be summary and my feature aspects. So people already know that what is the materials. So the layered materials consist of two-dimensional platelets. You can see the different layers. So that are weakly stacked together to form a three-dimensional structure. So this is the graphene structure. So each layer consists of strongly bonded with atoms and weakly attached to the sheets above and below to the van der Waals force. So this weak interlayer, so we can exfoliate and we can separate by the single layer. So the single layer performance are better than the bulk. So how we are going to fabricate and how we are going to make the devices based on the single layers and the few layers. So this will give application in the phototransistor, optical sensor, LEDs, laser, and high electron mobility transistors. So because of these dimensional properties, so the first 2D materials was invented in 2004 by these two professors in Manchester from the graphite. So here is a simple examples. This is people they used the Scotch tape, the simple Scotch tape with the piece of graphite, and they got a single layer graphene, and they got a Nobel Prize in 2010. So from this, so people they started with different kind of 2D materials. So for the different applications. So because of this monolayer, atoms tightly packed into the two-dimensional honeycomb lattice, and it has a tremendous development in the material science because of the unique novel and the electrical and the mechanical properties. But the main drawback of this graphene is that it has a absence of band gap, and there is no clear on-off state, and it has a weak light absorption. So because of this drawback, so people they have go for the choice of another 2D materials. There are number of 2D materials we can choose for the different kind of applications. So the TMDs, this is the transition metal dichalcogenides, is mostly semiconductors. It has a different band gap. So we can choose for what applications we want. So if you are choosing for the visible range or near infrared or IR range. So we can choose a particular material for the particular applications. And the HBN is a dielectric material, and another is a black phosphorus. This seems to be the same properties like graphene, but it is a semiconductors. So still there are many layered materials. So if your material is a direct band gap, it has a very good applications for the features, and it has a these devices we can use for the circularly polarized light and electronic devices. So these are the different kind of materials available in the commercially, or we can grow in our lab. So mostly people they used the MOS2 and the GASE and the SN, the tin-based materials. So the single layer nanosheets, it has a good property for the atomic electron confinement, and it has it will give the superior electron mobility, and it has a good electron transfer platform, and because of the good light absorptions, it has a high photo response, and this is people made for device will be good performance for the photo detectors. So not only the single materials, we can combine the two different materials for the heterostructures. So people they can use for the two different materials. Suppose if you have a P-type material and the N-type material, we can combine, and we can have a PN junctions. Otherwise, we can use a 3D materials and as well as 2D material. For example, if you have a silicon substrate, and we can fabricate a 2D material like a MOS2 or a graphene. So with the silicon and the graphene structures. So this heterostructure we can fabricate in the lateral heterostructure or vertical heterostructures because of the applications. So if you want a lateral heterostructures, we need to transform the setup, and we can have a lateral heterostructures. So this kind of heterostructures, it has a high carrier transport and it has a sharp and clean interface. So I will show the optical microscope images, these interfaces, maybe in the future slides. So now I can move into the experimental sections. How we can grow this kind of materials and how we can fabricate. So this kind of crystals we can grow. There is a two different method. There is a chemical method and a physical method. In the chemical method, we can use the CVT, chemical vapor transport, and the Bridgman technique to grow the single crystals. From this method, we can use a mechanical exfoliation technique, liquid exfoliation technique to get a monolayer or few layer or bulk. So in the physical method is a CVD and the PVD. So here we can grow the single layer on the substrate. So here you can see that this is the bulk crystals we grow in our lab, and using the Scotch tape, we can exfoliate multi-layer, few layer, or monolayer. So just I will explain the CVT grow methods. So in this method, we have the quartz tube with high vacuums. We will keep our samples here, and the iodine is a transport agents, and we will in the one end we will apply the high temperatures. So in other end it will start to grow our samples. Like there are variety of consistent metal dichalcolinate like MOS2, MOSE2, whatever MOTU2, and other materials. So this method, it has a convenient to operate and the crystal growth at low temperatures. So only drawback of this method is the crystal size is very small. So we have another technique, that is the Bridgman technique. It is the same like CVT, and here only the Bridgman technique we will use a high vacuum, and it has a high melting point. So we can grow the same crystals with a large size. So after growing the crystals, how you can have a single layer, because the bulk material we can keep in the Scotch tape, and we can rub and slicing slowly many times, and we can repeat the process, and we can have so many area to transfer on the substrate. So once you can transfer on the substrate, we can see the different kind of layers. So from optical microscope and the Raman and the PL measurement, we can distinguish the different layers, even the single layers. And the AFM, atomic microscope, is used to identify the thickness of the layers. So now I will explain how we can fabricate the devices using this exfoliation technique. So after exfoliating our 2D material on the silicon substrate, we can see the flakes. So this is not a single layer, it's some few layer. So then we have a TM grid as a mask patterns. So actually this is the shadow mask. There are different kind of techniques. This is the shadow mask technique, and we can align this TM grid under the microscope with the manipulators, and we can have this sample holder to fix where we want to put our electrode. So this is after electrode, you can see the devices. So with the electrode patterns, so mostly the electrode pattern we will use the thermal evaporator. We will evaporate gold and chromium. So after the final device, you can see the channels, and this is our materials. So here the source electrode and the drain electrode. So this is a simple technique. We can start with this. So after that, so we can see the different kind of devices. So this is a simple one material, whether it is P-type or N-type. And here you can see the PN junctions. So the lateral van der Waals heterojunctions. And if you want a vertical van der Waals heterojunction, you can see this one with shadow mask technique. So the another technique is a photolithography technique. Here we can see that first we will make this electrode with the photolithography. After that we can transfer our material on the electrodes. So this is also simple. And the another complicated method is e-beam lithography technique. So here we can go the channel length will be around 10 nanometers. So even the small flakes we can make our devices. So here you can see that there are, after transferring, so there are many kind of flakes with the different thicknesses. So how many thickness you want for your applications we can choose, and we can use this e-beam lithography for the electrode fabrications. So from these introductions and experimental sections, so I will conclude this part. So you can take these messages from this fabrication technique. So we can grow the single crystals, or we can commercially buy the single crystal from the company. So then we can use a Scotch tape. So after exfoliation, you can see the single layer graphene with different optical contrast, and we can confirm through the Ramans. So then we can use the transfer system to make our electrodes, the very good electrodes. So here you can see the example devices. So the final device looks like this one. So this is the one. So now we can go into the application of this 2D materials. So I will present this work. So previously people, they used only the binary compound like MOS2, MOSE2 and MOTU2, and in the starting actually we try to make a ternary compound. So ternary compound actually we try to do with the many combinations. So we success this tin based materials. So why we choose this tin based materials? Because we can tune the band gap. So for particular band gap, we can choose the particular material for particular applications. Here we used this material application for the photo detector and the photo transistors. So here we can see the MOS, how the first publication from this 2D material came for the MOS2 transistors. So here we can see that after exfoliations on the silicon substrate, we have a different kind of thicknesses, and they choose to only this single layer. And here they made an electrode, and they study the transport and the photo transport properties. And this mobility, you can see the 4.0, and the responsivity, you can see the 800 ampere per watt, and it has the rising and the decay time is 4 and 9 seconds. So in my case, I choose this tin-based material. So here you can see the crystal structure and the XRD after growing the single crystals. So here the scanning electron microscope image, you can see the different layers. So this is a TEM for confirmation of this material. So after fabrications with the electrode, the final device is like here. You can see the thickness of this flake is 6 nanometer. It's around 10 layers. So this is the optical microscope images of my devices, and this is my device schematic structure. The silicon substrate and dielectric silicon dioxide, and we will transfer our material, and after that we have a electrode in here. This is the source and drain electrode, and we will apply the laser light on top of the materials. So here we can see the transport properties. So this IV curve, it shows the fabricated devices, it has a ohmic contact with a different gate voltage. And for the mobility from this IV curve, we can see the 4.6, and it has an on-off ratio, it is 10.6, because you can see the IV curve in the dark range, as well as it is when we apply the laser light, it has a high increase in the mobility. So then we can study this, not only the electrical properties, the optical properties, to measure the photo response of these devices. Here see the different laser power, we will get an IV curve like this. From here we can calculate the responsivity. So the responsivity of my device is 4,480 amperes, 4 4480 ampere per watt with the low power. Usually the responsivity will be higher in the low power. And from here we can calculate the device detectivity. So detectivity, it is in the zones, and this is the rising and the falling times. For my devices, 9 millisecond and 8 millisecond. Usually this is the high response in the compared to the previous MOS device. So the same device we can fabricate instead of silicon substrate with the flexible substrate. That is the PET substrate, and we can have a flexible photodetector. So this is the flexible devices without bending, and we can bend with the different angles, and we can calculate the photo response, how the devices people are using for the smartwatch and other applications. So this is the one. So this is the one part we can use 2D materials for the single materials. So now we can combine this kind of 2D materials with another substrate like heterojunctions. So here what we have done, we combine our single layer MOS2 with the P-type gallium nitride. So the gallium nitride is a P-type material, and the MOS2 is a N-type material. And in between we have SiO2. This is just for dielectric for LED applications. Here I will explain. So here you can see the P-type gallium nitride, and we grown SiO2 with atomic ALD technique, atomic layer deposition technique with few nanometers. Then I will transfer our MOS2. So here we can see the MOS2. So of the top of MOS2, I have a single layer graphene. This is just for a electrode, electron injections from the electrode to my this N-type material. So then I have two electrodes. This is a source and a drain electrode. This device actually work for both the light detections as well as light emissions. So that's why this is a diverse functionality. So I will explain. So it has we can have a multifunctional. That's why people they will call it as dual functionality, the same device structure. So this is a schematic device of my structure. You can see the P-type gallium nitride, MOS2, graphene. So this is. So here actually we didn't use a mechanical exfoliations. Here I used the CVD grown MOS2. Then I used the wet chemical transfer technique. So here we can see the photo detector part. So just when we are applying on the laser light, that is 633 nanometer lasers, then we can have a IV curve. We can see the heterojunctions. So it has a very good PN junctions. So from here we can see the different laser power. We can have a different responsivity. The responsivity for the heterostructure will be very low, because when we are applying the lasers, there will be electron hole pair injections in this N region and P region. So this is the. So finally we got in the falling and rising time, it is in the second range. So this is the self-powered photodetector. Even without applying any bias, this device will work for the photodetector. And this is very important for these devices. Actually, this device will give the electroluminescence when we are applying the bias. So usually we will give the forward bias for the electroluminescence for the LEDs. So when we are giving with a different bias, we can see the emission from this MOS2. It has a red color emissions in the around 650 and 700 ranges. So how we can explain this device performance in the physically the physics? So when we are giving the reverse bias, the electron hole pair will be separate from here. So that means it has a photodetector properties. When we are applying the forward bias, there will be a electron hole pair accumulations at the silicon dioxide. So here we have emissions from this range. So this is the importance of this work. So now we can go into the two different kind of 2D materials combinations. That is a SN2 and GASU. GASE is a P-type, and the SN2 is a N-type material. So here we can have not only these not only two materials, we can combine many materials, even so many combinations we can make for the particular applications. So here I can see I will give the optical microscope image. This is a P-type material and this is a N-type material, and these are the characteristics of this material. So now we can have the electrical property. So after making the electrode, so when we can have when we are applying the bias, we can see the PN junctions. So from here we can have the rectification ratio is 10 power 5, and with the gate voltage is minus 30 volt. So this is the photo response of these heterostructures. So just I will explain what is the photo response. So when we are applying the light on our device, there will be electron hole pair separations. So this is from here how the electron hole pair are separating and how you are detecting the curve. So from here we can calculate our photo detector and the responsivity. From here we can calculate the quantum efficiency. You can see the quantum efficiency of this device is 62%, and the detectivity as well as the time response curve. So not only this photo detector, actually from these PN junctions, we have measured this one, the solar cell property of this particular combination. So the first, actually we got a very good efficiency from this these 2D materials, because even though we compare to the other solar cells, it is a very low, but among these 2D materials, it is a little higher, 2.8%. So the same device we can fabricate on the flexible substrate, and we can measure our photo detector as well as the electrical property. So these are the summary of this talk. So, and I will go into some of the feature aspect. So the summary, actually we have this tin-based materials and the 2D and the 3D combination, and the 2D and the 3D material combinations. So in future, actually we are doing the 2D quantum dot. Even we can make a quantum dot with the MOS2, WS2 and these kind of materials, and we can have a combination of 2D and the quantum dot combinations. So this is another feature. We can have a message from here. So we can have N-type materials, and there are many other combinations. Here we can have even N-type and N-type combinations. We will call it as isotype. Even P-type and N-type combinations, anisotype, PN junctions, and the graphene with our N-type material. This is iso anisotype combinations. So we can have a different kind of combinations, and for this combination, you need to draw the band alignment. So where is the electron and the hole will be there, and this Fermi levels. So we can tune this Fermi level for your applications, even the photo detector, LED, whatever the electron transistors. So and here is another kind of devices, that is the black phosphors and the single layer graphene combinations. Usually the black phosphor is not stable in the air, so how we can make a stability in the air? So I will transfer single layer graphene on the top, then we can have a stability issue we can solve. So from these combinations we can have devices like, so here we have one more electrode and here another electrode, then we can have a different laser to excite the black phosphors. So here we can see how we are measuring the probe. There is a heterojunctions here, and we are applying the bias from these probe stations, and we can have a IV curve and a time dependent phenomena. And here we can explain the physics. So what is the physics behind this black phosphor and the single layer graphene? Is usually previously it was a photo detector, and here we have the photo gating phenomena. So here when we are applying the bottom gate voltage, there will be electron hole separation, and we can have a measurement in this. So this is the photo response of this graphene and black phosphor combinations. So these are the acknowledgement, and yeah, thanks for the committee to discuss about my talk. And if you have any questions, you can ask.
Thank you, Dr. Bhagiraj, for such a wonderful and interesting session. Participants, if you have any clarification, kindly mail him. We will get you his mail ID. Thank you, sir.
Okay, thank you.
Pakiraj, thank you, Pakiraj. Really nice presentation. Pakiraj, is it audible?
Yeah, I can hear you, sir.
Is it audible?
Yeah, I can hear you.
Thank you, Pa. Thank you very much for your
Thanks.
nice presentation. Okay. Thank you.
Okay, let's see.
I request Dr. E.R. Balupriya, Assistant Professor, to give her presentation. And now I request Dr. Nimesh Anvaraju and Dr. S. Saranarasu to handle this session.
Hello. Sorry. Oh, sorry. Sorry, that 30 minutes now. Okay. So actually நானே கொஞ்சம் புரியலங்க. என்னதான் சொல்லுங்க. இல்ல ஆக்சுவலி இது ஆமா.
Excuse me, sir, it's not audible.
Am I audible now? So my topic is recycling of microwaves as low-class refractory carbon materials for fabricating supercapacitor electrodes. The content of my presentation includes some motivation, objectives, experiment part, results and discussion, conclusion, and finally scope of the future. My motivation includes since last decade, material scientists they are attracted towards biomass and more specifically phytomass. Phytomass means mass of living and dead plants for producing value-added materials.
It's interesting to know that more than half of the world's agricultural phytomass have been cropped. Firstly, the omnipresent and plentiful agricultural dispatch effectively, they offer a secondary and inexpensive and renewable source of carbon. The present scenario, the landfills which have already become flooded with the non-renewable garbage, they do not admit solid anymore, and consequently, we have to propose some ways of segregating, recycling, upcycling, and reuse of these waste for reducing disposal problems and improving our nation's economy. So that the waste biomass should be seen as an unexplored resources as well as zero gas source of essential environmental services and not as waste at all. So that's to provide biomass waste recycling based concept having great potential in reducing environmental issues and climatic issues for initiating. We have initiated the circular bioeconomy and green energy processes attempted. The objective of the work is to evaluate the performance of concentrated distilled for activated biomass carbon for the possible application electrode capacities. Next, to adapt to investigate activated carbon relevant physical characterization studies as well as capacity of the influence cyclic volumetry and GCD technique. Next is adapting technology and recycling the circular bioeconomy to establish energy from waste concepts. To establish an effective path towards achieving waste, we have a value-added product that is filter waste. Now we should see what are the electrode materials, promising electrode materials for supercapacitors. So it includes carbon base that is activated carbon from biomass that we have chosen. Transition metal oxides, conductive polymers, metal oxides, carbon composites, conductive polymers, carbon composites, hybrid metal oxide, conductive polymer materials. So, activated carbon are much cheaper than metal oxides and conducting polymers and have a specific surface large surface area larger than the later. So, world demand for activated carbon is forecast to expand by 9% per annum to 2014 to 1.7 million metric tons. Activated carbon can be managed from food and food and agriculture economy, but it was thus they were apparently reaching carbon content for producing activated carbon products that lead to less cost alternative for commercial carbons utilized for the energy storage applications. So this plant biomass that is biomass includes different parts of the plant such as stem, leaf, flower, seed, fruit, etc. So we are going to see the excellent performance of all this biomass ecological properties and electrochemical properties. The biomass selected is Indian short, that is ISAC. It is designated as Indian short activated carbon designated as ISAC. So botanical name is Cananica. The D short portion that is taken from MBA campus Madurai. So this flowchart shows how the activated carbon is prepared. So collecting and washing and activating it sulfuric acid, then finally after washing and drying you get the activated carbon. So what are the characterizations given or electrochemical characterizations given? Also the electrochemical characterizations given. So it is electrolyte uses 1 and mixture. So in addition to carbon, significant percentage of hydrogen and oxygen in the sample, it shows the presence of various organic functional moieties present in the sample. So this shows the case analysis of the broad peak through the reflections corresponding to rapid phase which may reduce to the amorphous nature of the sample. So this may offer to capacity pieces of the sample. So the stem picture shows that the standard structures with a very particular shape, so it can be modeled at systems for activation enhance the preparation of rigorous material and the aromatization of the carbon filter resulting in the creation of porous structures, which is the platform for high electrochemical capacitance. So this is good version. The term has a high bit value and pore size is 3.8. So This was the Wikipedia vibration release. This was the various functional groups present in the sample. This is the electrochemical features of the sample collected. So this is the cyclic autogram of ISAC. So the CV picture in acidic solution was the increase of the electrochemically accessible surface area of these highly coiled carbon, which leads to quick charge preparation. So the scan rate is given and the capacitance value is given. So this finally we can conclude that this sample shows a good electrochemical performance and has potentially application as electrode candidate for supercapacitors. Thank you. So it is based on circular bioeconomy process.
Thank you, madam. We are running out of time, so let us call upon the other paper presenter they are coming in the online mode. Thank you. Rani Mariam is in the online mode.
Yes, sir.
Yeah, please share your screen and start your presentation.
Am I audible?
Yes.
Is my screen? Am I audible? Hello, sir. Is my screen visible?
Not yet, ma'am. Please wait. Rani Mariam
Am I still not visible?
I think the screen is not visible.
Okay, let me see. Am I now visible?
Yeah. Yes, we can start.
So can I move to my presentation?
Yes.
Okay, thank you. Good afternoon all. I'm Rani Mayam Surya, Research Faculty at CMS College, Kottayam, here to have a presentation on the topic spectroscopic investigation and quantum chemical calculations and molecular docking studies of antibacterial agent for methyl sulfonyl benzaldehyde. So this is the content of my presentation. I will be going through the aim and objective, experimental and computational tools, importance of the study, geometrical optimization, vibrational analysis, homo-luma analysis, O2 docking, antibacterial study, conclusion for the scope of the work, and reference. Is my screen not
Excuse me,
moving?
ma'am. Your slide is not moving.
Let me see what happened.
Your slide is not moving.
Yeah. Wait. Let me see.
Yeah, please continue. Yeah.
Okay. I'll be going to the importance of study. I think still it's not moving, right?
Now it is experimental technique.
Okay. Okay. I will do it from my mobile. Is it doing now?
You can directly go to results.
Okay, fine. So basically, when I talk about antibacterials, people used to ask me why antibacterial. Thing is that
You
the
can go
cannabinoids and
directly go to the results.
okay, fine. This is my compound with about 20 hydrogen atoms. It was purchased from Sigma Aldrich. And first of all, we have done the optimal geometrization. From that, we were able to study that it was having the CC bond on the either side of the aldehyde group are approximately greater than the CC bond in the ring due to the resonance effect between the aldehyde group and the phenyl group. And this is the IR spectrum of my compound. Here we have the experimental, the calculated, and this is the Raman spectra, calculated and experimental. From the vibrational analysis, I was able to say that the strong and simultaneous activity of CC mode in IR or Raman spectra is responsible for the intramolecular charge transfer. The observed band at 1292 in IR is assigned to SO2 and asymmetric searching mode, and the high intensity peak at 1149 in IR and 1149 in Raman correspond to the SO2 symmetric mode. The intensity enhancement of SO2 stretching wave is due to the conjugation with phenyl ring. And the CC stretching is appeared at IR at 1702, and the Raman counterpart is observed at the same wave number with a strong intensity. The lowering of CC stretching wave number is due to the conjugation between the carbonyl group and the aromatic ring. The charge transfer interaction. The charge transfer interaction between the aldehyde group and the methylphenyl moiety through the phenyl ring is provided by the C double bond S stretching in IR. C double bond stretching vibration is found as intense band in IR at 821 and counterpart in Raman appeared at 842 with an increase in its intensity. So this is a HOMO-LUMO structure. We can see HOMO is having an energy of minus 0.33 electron volt. LUMO is having 0.198 electron volt. And the energy gap is 0.135, which is smaller. So moving to the molecular docking studies. The structure of E. coli DNA gyrase was downloaded from the protein data bank, and the protein preparation was done using the reporter structure protocol by removing the water molecule and all the natural ligands to clear the active site. The grid was set to its cover the whole region of interest in the macromolecular, and protein was saved in PDP-QT format. The optimized structure of MSB was converted into PDP format, and the ligand preparation was carried out and recorded as PDP-QT. Both the protein and ligand preparation were carried out with the BioStudio, and the molecular and docking interaction of MSB, that is my compound, with E. coli bacteria were evaluated, and the green dashes line shows the hydrogen bonding between the compounds and amino acid, and pink lines show the hydrophobic interaction. The interaction type between the protein and the ligand are indicated where 3 conventional hydrogen bonds were observed in the active regions with the binding affinity of 5.3 kilocalorie per mole. Additionally, in figure, we can see other type of bonding also. As a result, the theoretical in silico based molecular docking scores support that MSB is a good potent for inhibitor. This figure, we can see that my compound, that is our compound, is docked with the docked with the E. coli bacteria. 3D structure is shown in the left side, and the 2-dimensional structure is shown on the right side. Here we can see that the green dotted line shows the hydrogen bonding. And this is an experimental study of antibacterial activity. MSB was screened for the antibacterial activity at agar diffusion, well diffusion method, and the activity was observed at the emission zone. And bacteria strains were screened against E. coli and Streptococcus aureus, and the compound shows good activity against the bacteria. In this figure, we can see that my compound was studied against 2 bacteria, and it's showing antibacterial property. And we were also compared with the standard antibiotic streptomycin. And The conclusion, the phenyl ring and methyl moieties of non-planar and red shifting of C double bond stretching V number is due to the conjugation between carbonyl group and the aromatic ring. Simultaneous occurring of CC provide evidence for the charge transfer interaction, and the lowering of HOMO and LUMO energy gap is clearly explained the charge bond interaction taking place within the molecule. In addition, in vitro antibacterial activity against E. coli and S. aureus showed that MSB exhibit antibacterial activity. Molecular docket studies revealed that the various interaction tightly empowered the MSB to active site, which could well explain the excellent antibacterial activity. So this is for the scope. This result shows that MSB or its derivative can be considered as a useful template for the development of antibacterial or potent agents. The derivative with enriched SAR, surface activity relation, may lead to the further rational development with a novel mechanism of action to overcome the drug resistance. In the near future, number of derivatives could be definitely emerged as a first-line therapeutic agents. And these are the reference. Thank you.
Thank you. Yeah. We are running out of time, so let me invite Sri Lakshmi.
Yes, sir.
Yeah, please take it first.
Okay, good. Thank you. Okay, visible, sir?
Yes, visible. Yeah.
Okay. Good afternoon, all. Growth. Today, the topic of my presentation is spectral characterization of organic single crystal 2-aminopyridinium hydrogen phthalate, a promising candidate for NLO applications, under the guidance of Dr. C. Ravikumar, Assistant Professor, Department of Physics, CMS College, Kottayam. These are the outlines: introduction, crystal growth, resultant discussion, conclusion, and reference. First is introduction. The compound name is 2-aminopyridinium hydrogen phthalate. The structure of the compound was reported in September 2019 by V. Shiva et al. In active crystallography. It is a pyridinium derivative, and most of the pyridinium families are considered to be good NLO materials. And the okay.
Could you show your results directly?
Okay.
Present your results directly.
The resultant discussion. First one is XRD studies. The ground crystal structure was confirmed by powder X-ray diffraction studies. This is the powder X-ray diffraction pattern of 2-APHP crystal. The sharp peaks in PXRD confirmed the crystallinity nature of the ground sample. The obtained lattice parameters are good in agreement with the reported values, and these values confirmed the crystal is in compound is in monoclinic crystal system with the space group P21. And next is quantum chemical computation details. The optimized structure of 2-APHP determined using DFT method with the B3LYP 6311++ GDP basis set using Gaussian Knot-9 program package. And this is the optimized molecular structure of 2-APHP labeled with the atom numbering is shown in this figure. And next is optimization table. A few selected experimental and geometrical parameters are included in this table. The calculated bond length of N7H13 and N7H14 are found to be 1.006, 1.0394 angstrom respectively. The elongation of bond length N7H14 reveals the possibility of NHO hydrogen bonding. The bond angle of C1 into C3 shows a markable variation from the ring CC bond angles, indicating the presence of an imperfect hexagonal geometry in the 2-APHP molecule. C1N7 bond length is decreased from the other CN bonds within the pyridine ring due to the mesomeric effect. Next is vibrational spectral analysis. First one is FTIR spectra, experimental and theoretical. Next is FT Raman spectra. Next is NH2 vibrations. The strong peaks in IR at 3370 and 2978 corresponds to asymmetric and symmetric stretching vibration of NH2 group. The redshifting of NH2 asymmetric stretching wave number is due to the formation of intramolecular NHO hydrogen bonding. The very strong peak present in Raman spectra at 1596 arises due to the NH2 scissoring. The NH2 rocking modes are observed as strong band at 1048 in Raman and as weak band at 1046 in IR. Next is carboxylate vibrations. The strong Raman band at 1490 is assigned for the asymmetric stretching vibration of COO-. The reduction in COO- asymmetric stretching wave number and its enhanced intensity denotes the hydrogen bond formation. The strong IR band that arises at 1447 reveals the COO- symmetric structure. The blue shifting is due to the intramolecular hydrogen bonding formation. And next is carboxylic vibration. The weak band centered around 2916 in IR spectrum corresponds to OH stretching vibration modes. The redshift of OH stretching wave number confirms the hydrogen bonding in the molecule. The OH in-plane bending vibration is observed at 1467 as strong IR band. The upshifting of in-plane bending vibration points the intra and intermolecular hydrogen bonding formation. The strong intensity bands observed at 1684 and 1667 are assigned to the C double bond O stretching mode. Next is pyridine ring vibration. In the present study, the CH stretching vibration is observed as a strong IR band at 3184. The corresponding Raman counterpart is identified at 3178. The strong peaks in Raman at 1128 confirm the presence of CH in-plane bending vibrations. The strong peaks observed at 928, 860 and...
Please conclude your work.
Okay. The second harmonic generalization. Okay. Conclusion: the 2-aminopyridinium hydride cartilage crystal was successfully grown by slow operation technique. From XRD data, it is observed that the grown crystal belongs to monoclinic structure and non-centrosymmetric space group P21. The redshifting of NH2 asymmetric stretching wave number is due to the formation of intramolecular NHO hydrogen bonding. The blue shifting of the COO- asymmetric stretching is due to the intramolecular hydrogen bonding formation. SHG has been confirmed by Quitz powder technique. The laser damage threshold value was found to be 8.43 joule per centimeter square, which is larger than KDP and other NLO materials. The above experimental result shows that 2-APHP crystals may have some NLO applications. Friends, thank you.
Let us congratulate both Rani Mariam and Sri Lakshmi for their wonderful presentation. Now let me invite Begum Vilarasi from Anna University. Begum Vilarasi from Anna University is there.
Begum Vilarasi, madam.
Begum Vilarasi. Yeah, please share. Okay, yeah. Your screen is visible here. You can start your presentation.
Ma'am, start your presentation, ma'am. Yes, ma'am.
Yeah, you can share your screen, yes. Your voice, we are not able to hear your voice. Share your screen.
Ma'am, you are not audible.
You are not audible. Check your mic. Please unmute.
Please turn on your mic, ma'am.
Yeah, please continue.
Ma'am, try your mobile also. Through your mobile also you can make a call. Use your mobile to attend this meeting so that you can present.
Madam, thank you.
அப்புறம் சாவி அதில் விட்டுருங்க நாங்கள் எடுத்துட்டு அங்கே மால்ல எல்லாம் பண்ணுவோம் தெரியுங்களா அதுக்கு ஒண்ணு சரி நான் பண்றேன் நீ அது பே பண்ணாலே இதெல்லாம் இருக்கு
Others, please mute your mic. Paradise. Madam, thank you. Voice மட்டும் வாங்க வாய்ஸ் நான் போன்ல ட்ரை பண்ணுங்க போன்ல கூட பேசலாம்
No, ma'am. Still you are not audible. Okay, ma'am. You have tried your best. Thank you. Participants, now you have a lunch break. Please join at 2:15 for the next session. Ma'am, presenting the slide is not the problem. Your voice is not audible. That's the problem. Thank you, ma'am. Thank you once again. Participants, now you can leave the hall and rejoin after lunch exactly 2:15.
crystal is identified using the measurement, and this blue
Good afternoon to all. Let us resume our technical session on recent trends in material science after the group dance. I cordially invite Dr. M. Anthony, Assistant Professor, Department of Physics, Anandar College, to introduce the resource.
Good afternoon. I am honored to introduce today's resource person, Dr. M. Jayanath, Assistant Professor, Department of Material Science, School of Chemistry, Madurai Kamaraj University. He did his undergraduate in physics at ACM College, Madurai, and MSc Physics in Madurai Kamaraj University, and another master's degree in the National University of Singapore. He completed his doctoral research in University of Oslo, Norway in 2007. He worked as a postdoctoral fellow in University of Paul Season, France. And he further continued his research career as a postdoctoral fellow in Mexican Technological University. And he worked as a research scientist in IME, Norway, from 2008 to 2010. To his credit, he was recognized by many awards as and a credit, namely Research Fellow in National University of Singapore, an Norway Research Council Award, CNRS France Research Fellow, Young Scientist Award from DST, a Raman Postdoctoral Award from UGC, and a DST Grad Fellow. He is also a life member in Material Research Society of India, Semiconductor Technology of India, and the Solar Energy Society of India. He conducted 6 international conferences. He has completed 6 PhDs, and at present 4 researchers are doing their doctoral degree under his guidance. He guided 12 young students, and he completed 2 research projects, DST SAP and DST Dept, and 3 ongoing research projects in SAP, IUAC, and RUSA. He served as a NIR member at Madurai Kamaraj University. To his credit, he published more than 150 research articles in peer reviewed journals. He acquired high research knowledge in energy materials, thermoelectric, semiconductors, and nonlinear dynamics. Now invite Dr. M. Jayanath to deliver his research article. Over to Dr. Jayanath.
Thank you, sir. I request Dr. K.S. Joseph Wilson, Head of our department, to honor Dr. J.D.R. Prayari. Thank you, sir. I request Dr. J.D.R. Prayari, Assistant Professor, Department of Material Science, to give a talk.
A very good afternoon. Let me first thank for the nice introduction by Arul. It was nice introduction. And I also would like to thank Mr. Watch and Head of the Department Wilson for having me here for a presentation related to the details. So I have given my talk in the title of materials for first and third generation process. So it's a very broad title. But today what I'm going to do is I'm not going to be very detailed about my research work. Some of you are, most of you are from master degree, and I don't want you to make you sleep. So I want you to get a bit awake. And after the lunch break, it's always very tough job to hold you from sleep. So I think you have heard from yesterday onwards, we have been hearing about many different materials. So today I will be mostly focusing on solar energy. And among the solar energy materials, I think I have mentioned about first and third generation only, and I'm not going into the details about the second generation solar cells. In the first generation solar cells, it's mostly made from silicon layers. I think you will have a chance to look at how the silicon layer will look like. My student will give you a chance to look at these layers. And regarding the third generation, in the third generation, I will first tell about what is first generation solar cells, how it is made, and in that particular type of solar cells, what we do in the research aspects. So how we are tailoring its properties and how we are upgrading the efficiency, that I will focus. And then what are the problems in the first generation solar cells and how it can be removed or remedies of the first generation solar cells will be applied in the third generation. So let's move into the title. So I think don't worry about the many of the things here, introduction to the energy, and I will just give a classification of energy sources that are available and what are the alternative options, and for the alternative options, what would be the desired characteristics. And in that, I will also talk about the basic theory of any type of source. Should I need to continue only in English or should you need a combination? This is a first one. So I will keep it in English. So you see that you have a basic criteria for solar cells, and then we will see a movie on how the solar cell is fabricated. Okay. So introduction and energy and environment are the essential sustainable thing for the development of the society. So we are really in the crisis of energy. And why? Because of the depletion. Most of the natural resources are getting depleted. So we are in the urge to look for different or alternative types of energy, which could be quite useful or could be renewable sources without any impact on the social aspects. So that is how the energy demand is needed. And in terms of resource availability and trade, environmental limitation, technological development, this is not a local problem. This is a worldwide human related problem. So energy is really a problem because of our necessity. Every day we are using different type of sophistication in our life. So we would really like to use many different devices which needs energy. So that is where the main reason comes into play. And this was being also said by the German Advisory Council of Global Change that we will be depleted all resources, natural resources like gas, coal, and oil. And in 2050 onwards, I think we will be widely utilizing only the solar electric energy. So which comprises of photovoltaics and the solar thermal generators. So what are the global energy sources that are available in day-to-day life? It can be classified into two different categories. One is primary and the other one is secondary. And in primary, we can again classify it into two different. One is conventional and alternative energies. So I think you all know this. And in the alternative sources, I think it can be classified into solar energy, wind energy, and the hydro energy, tidal energy, and geo energy, and biomass. So among all these, today I will be only focusing on the solar energy related aspects. So what are these? How good the characteristics of these materials or this energy should be? It should be abundant. So it cannot be depleted. For example, coal and oil and gases are getting depleted once we are utilizing them. But for example, if you take about sun energy or wind energy, you cannot deplete So such abundance is very much essential, and this should be renewable in nature, and it should be environmentally clean, and it should have a high energy content, and it should be very low cost, and it's easy storable, and other aspects or characteristics are very essential to go for the alternative energy system. And next comes to the why should we consider solar energy? Why we are very much focusing on solar energy? Because we are gifted that we people are located exactly near the equator region, where the solar light is very effectively radiated in every day. So we could really make use of that solar radiation. So that is where we are gifted, especially those people who are located in the equator region. And if you think about what would be the irradiation, so if you meet other, the earth receives 173 kilowatt of energy from the sun. So if you can capture 1 hour of energy, you can use that for 1 year. That is impossible, but in the theoretical aspects, if you could capture 1 hour of energy from the sun, you can really use it for 1 year of the whole world. So that was the scenario. So if you could capture so for example here I have 6. So if you energy for the surface every day, if you capture 1 day energy, that can be placed for almost 60 years at present rates of inflation. So this is really an important aspect. And in the sun, you have both heat and light energy. And in the heat and light energy, you will have different types of process, whereas photosynthesis, photochemistry, and photovoltaics. And we will be only focusing on this photovoltaic, where there is institution. So moving on to the main concept of device, what is a solar cell? A solar cell is nothing but a device that converts light energy into electrical energy. So that is the device. And here I have given you a single junction plain silicon based solar cell as a pictorial. And how this solar cell is constructed? It is construction of PN type silicon, like here. And you have when the connection is made, you all know that you have a depletion region here. And this cell is in top, you will have a silicon nitride layer and contacts with there. When the sunlight hits, the photons which are radiated on the cell will convert them into an electrical target like electron hole path, and this will be connected to the device. So this is the simple construction of any solar device. If you have this one cell, if you have looked at the panel, I think in somewhere you might have looked at many different panels. Each panel will have several cells. So if you make one of the square, that is one cell, and if you make an array of cells, then that is called as modules. And in the solar spectrum, you have the different kind of energies are irradiated at different level, and you see this is the wavelength in the x-axis and the energy irradiations at the y-axis. And you see in the visible region is the maximum energy that is exhibited from the solar radiation. So if we could capture this energy that is very effectively, then you can convert them into so that would really give you a very nice amount of energy production. So furthermore, just to make sure that the solar energy potential is for solar plus is about 1.1 into 10 to the power 5 terawatt, and 1 hour sunlight will be a annual global consumption. So, and solar energy conversion has different options like solar thermal, solar photovoltaic, and solar fuels, where this many of energies conversions can be made from sunlight. Okay, so there are currently 3 different generations of solar cell devices. So and they are classified based upon their material use as well as their limitations. For example, in the first generation for silicon wafer based solar cell, it is having one single band gap. When you talk about silicon, you all know the silicon is a semiconductor material which has a bandgap of 1.1 electron volt, and you can change this silicon into n-type and p-type by doping 5 elements like boron and phosphorus. When you try to dope boron into it, you can get p-type silicon material, and when you try to dope phosphorus into it, you will be able to get n-type. So in the first generation solar cell, you will have a single bandgap material and a single silicon based material as shown here, and this will yield a module efficiency up to 18%. And this technology has been still now we are only using the first generation solar cell, which has been widely commercialized and available for the market. That is to the general, and what is the problem with the first generation solar cell is you will have a limitation in the absorption of light because your bandgap is single bandgap, so you can capture only the solar radiations energy higher than that. So that was the main problem. So the first generation has a problem of single bandgap. To overcome that, people are trying to use the thin-film-based solar cells, where they can tune their bandgap. So you can tune the bandgap and make different junctions. Example of 2 junctions or 3 junctions or multiple junctions. That means you can alter the bandgap in a different way so that you can capture all the coming into your device. In second generation also, there is a problem. What is the problem is? The problem is when you try to make multiple junctions, you will have a phonon-induced scattering. That means you will have a thermodynamic release. So the heat will be produced, so the electron will recombine with the phonons, and that's how the efficiency is. So in first generation, you have a problem with single bandgap. In the second, so people move on to second generation. In the second generation, you have multiple stacks. Due to the multiple stacks, you will have a problem of thermodynamic. So in the third generation, people are trying to make quantum dots based or dye-sensitized based or perovskite based materials are used for making the access, but still in the third generation, you are very hard to control the size of the quantum dots or any nanostructure materials. So that was the issue with the third generation. So these are some of the examples of the devices. So this is a monocrystalline wafer, and this is the polycrystalline wafer, and this is the copper indium gallium oxide type wafers, and these are some of the gold-to-gold polymer based. Okay, now we have 3 generations. So if you want to make commercialization, what is essential? These 3 different aspects are very much essential. So this is taken from the scientist named Superman. He has been delivering a lecture at FPU, and we have followed this slide from here. So this is an efficiency, stability, and processing cost. If you have this 3 criteria, that means you will be able to commercialize the power line. And if you see the first generation and second generation products are also these criteria, and they are available commercially. You can go and buy them in the market, and it's readily available. And in India, if you see here, this is the renewable energy installation in India. So solar energy has been already installed up to 47%, and the energy from the wind as well, we are collecting total like 104 gigawatt per year. So this is how the renewable energy system is taken up. And this is a roadmap from the NREL, and this was delivered by Professor Martin, where he has been collecting all the different types of solar cells available in the literature, and he has been made this plot. And you see, this is the first generation solar cell, which has to 27% people have already reported, and this is an emerging technology where the third generation is also is almost 14 to 15%. So there are still a lot more work can be done to improvise the efficiency of the source. And this is the mechanical efficiency. So theoretical limit is almost 29%, and people have applied 25%, and you can see the multi-crystalline wafer that has been obtained 40.3% efficiency. So I was talking about that this is the production route for making different types of silicon wafers. So the first generation processor is made up of silicon wafer, and this silicon is nothing but sand. So they take the sand or pots, and then they can make different types of, depending on the quality of the material, they can prepare the different types of silicon, like the Tchaikovsky, proton, and multicrystalline wafer, and solar grade wafers. And this is the production line where you can have the chunk of silicon wafer and silicon melt, and then you can heat it into a redox, and then this can be cut into different blocks, and different blocks can be cut into wafers. Okay. So the basic criteria for making any type of solar, if you are going to make think about a single plant or a second generation solar cells or third generation solar cells, if you are able to keep these 3 points in mind, you will be able to do any type of solar. So what is this? So for the main essential thing of making a solar cell, the materials should capture all the incoming photons. So when you place your material, all the photons should be captured from the material, and that the photons will be effectively converted into electrical charges, either electron or holes. So this is the main point. So photon generation of mobile charge carriers and the efficient charge separation. How is it separated? When you have a potential, that means when you try to make a spatial separation by using a dopant, either by p-type or an n-type, then this efficient charge separation can be made and charge transferred to the external electrons and neutrons. If this 3 point can hold by you, then this requirement will lead to a simple design rule to keep in mind whenever you are designing a solar cell of any kind. You are kind of bored with it. So what I will do is I will just play a short video, then I will come back to this slides. Where?
To understand how solar cells work, we must look at the components of a solar cell. A solar cell is made out of a thin silicon wafer. When the sunlight hits the silicon in the wafer, photons transfer their energy to the electrons in the material. Electrons with increased energy tear away from the atoms, allowing them to move around the wafer. A controlled amount of boron has been added to the silicon in the wafer in a process called doping. Because of the boron doping, the silicon will easily get a positive charge. Similarly, the surface of the wafer is doped with phosphorus, and this part of the wafer becomes negatively charged. When electrons are torn through by the sunlight, the electrical field between the positive and the negative parts of the wafer will catch them, and this will cause a current in an external circuit. The efficiency of a solar cell is a measure of how much of the energy from the sunlight hitting the solar cell that can be transferred into electrical energy. We will now look at how the solar cells are made at IFE, but first we need an introduction to how a solar cell works. This is a schematic of a solar cell. The grey area is the silicon wafer. The surface of the wafer is doped with phosphorus. The blue layer is an anti-reflection coating and covers most of the front surface of the solar cell. But to lead the electrons out of the wafer, a grid of metal contacts is placed on top of the anti-reflection coating. The metal penetrates the coating and contacts the silicon below. This is the way plasma looks when arriving from the producer. It needs to undergo several processing steps before it becomes the finished solar wafers, multicrystalline and monocrystalline. Multicrystalline means that the wafer consists of a number of crystals with different sizes and orientation. Solar cells based on multicrystalline wafers are not as efficient as those based on monocrystalline wafers, which contain only a single crystal. But multicrystalline wafers do not put the same demands on the fabrication process, and are therefore easier and cheaper to fabricate. When the wafer is inspected and accepted for solar cell production, they are etched. After the etch process, the next step is to obtain an electrical field in the wafer so that a current may be generated when electrons are excited by sunlight. This is done by making a positive and a negative side on the wafer, or a so-called p-n junction.
The wafers usually come with a base coating of boron from the producer.
The purpose of the etching is to optimize the path of the light inside the wafer to gain as much current as possible. However, still some 15 to 20% of the incoming solar light is reflected. Now that the p-n junction is made, a so-called anti-reflective coating can be put on the front side of the solar cell. This coating helps capture even more of the light inside the wafer. On the front side, the contacts need to be as close to each other as possible to minimize electrical resistance, but at the same time far enough apart to let as much light in as possible. The solution is a grid type of contact. On the back side, it is common to cover the whole area with metal.
To get the contact through the reflection coating, we need to fire the contacts. We need to heat the contacts up. To optimize the process, we can change this the temperature profile, we can change the metals that we use.
The solar cell is nearing completion, but we still don't have full control over the excited electrons. To ensure that the electrons don't take shortcuts and create short circuits between the front and back contacts, an isolating trench is made along the edge with a laser, a so-called edge isolation. Now the solar cell is in principle finished, but
Okay, I think now we will be easy. This video will take me this job for me. So the main thing is 3 points. This is what the first thing is the wafer, which you can see the silicon wafer is like a mirror. It should be like a mirror. So if all the sun or the photon which is going to hit the wafer will be reflected. So if you want to generate more number of electron hole paths, your photons should be inside your wafer. To keep that, people will try to. So to keep that, people will try to make the surface permeable. Say that the incoming photons will be kept here because of the bottom internal. So that is where to photo generation of mobile charge carriers, minimum reflectance. And anti-reflect here you can do anti-reflection coating, excitation, or reduce or avoid staining. So when you make a contact on top surface, you also shade, you make a shade so that the light will not fall on the wafer. So that should be also reduced. That everything has to be optimized as such your wafer can be used very effectively. And avoid transmissions. That what does that mean is avoid transmission. So if your wafer is too thin, your light will penetrate and go out. So that is another case. So select a material with a suitable energy band. So if you could make this first part is very, very important. so that you can have a very efficient solar cell device. So the first point is very important. I'm just stressing that. And the second one is to make the efficient charge separation that you want to do a PN junction, because you will get a material from either a boron doped material or phosphorus doped material. So you start with the, for example, here what they have taken is here they have taken a boron doped silicon wafer and the phosphorus is diffused on top of it. So that is what has happened. And the third one is minimize the recombinations by avoid passive or passive material defects such as impurities, dislocations, grain boundaries, avoid surface recombination by passivating the surface. This are all done by coating silicon nitride on top of this finished PN junction material. And then the last one is avoid excessive resistive losses. The sun resistance will be high, series resistance will be low. So I think you know there's a ohmic contacts are made on top of this wafer, and the sun resistance are made because of when you are doping the front side, you may get some additional edge of the wafer. So you should be very careful and try to remove the edge of the wafer to avoid sun resistance. So the contact resistance and the contact design and substrate doping should be calculated precisely. And if you dope more, that is also a problem. If you dope less, that is also a problem. So you have to design suitable substrate doping condition so that you can have an effective and efficient solar cell device. So what we are doing in this, I think that is what. So this is the process flow. I think I will skip the process flow. So this is for the starting material. So you have a starting silicon wafer would look like this, and then you will do some chemical etching process to remove all this, and then you can make another chemical process with diluted sodium hydroxide and KOH that will yield very nice pyramidal structure, and then you can dope phosphorus using different type of diffusion conditions, and that will give you a PN junction, and then you can remove, and then you can coat the anti-reflection coating by using the silicon nitrides layer. And what we are doing in this case is for an ideal solar cell device, you will have a very nice IV characteristics like that. And this is the open circuit voltage of almost 0.6, and this is the short circuit current. It's maximum of 32 milliamps per centimeter square. This is an ideal that we have applied for the solar cell production. And this can be the circuit, when you put a circuit equivalent to the uptime IV characteristics, this will be a model of not only single diode, but you can have a double diode model with some sun resistance and series resistance. And what we do, so this is the standard solar cell wafer. So what we take is we take not the cell, we are making a PN junction, and then we try to make porous silicon on top of either porous silicon or form some kind of nanostructured silicon materials, and you can tune them with different colors. You see, this is all are made from porous silicon. And how this material can be, or these structures can be made, there are three different ways. One is electrochemical etching, the other one is metal assisted etching, and scaling etching. So we will see that. So these are some of the calculations that are essential for making the. So here is the electrochemical etching, ionization. So aqueous solution of hydrogen, chloride, ethanol, and ionic polarization is used. And metal assisted chemical etching is a procedure where silicon substrate partly covered by metal is subjected to etchant composition of hydrogen chloride and then oxidative agent. And stain etching is used with hydrogen chloride, nitric acid, and water to etch. So after the finishing of phosphorus doping, you take the wafer and then make a chemical processing to make different types of nanostructures. So that will give you an interesting result. So this is what we are working in our lab. And in here you see that the electrochemical etching setup, the mechanism, illustrated here. So this is the setup that we use it for making for networking structures or porous silicon by using two different electrodes. In between that, there's an electrolyte is used, and you have a platinum electrode on top and the copper plate at the vacuum side. And this is made in a tight Teflon beaker, and you can place them in a different way, and you will be able to see what we have. The other aspect is you have a metal assisted chemical etching. So what we do is we have taken the silicon and then you have a silver nitride with the nitride, and then this will after some time you will have the particles will be deposited onto the silicon, and then you try to etch it and then remove the metal that is present in their porous structure can be removed by using hydrogen nitric acid. And these are some of the literature available for many people have shown that for multi-crystalline. And what is important is what they have tried to show is the reflectance of the light is minimized after etching different type of material, and then you can see that the reflectance is minimized as much as possible. So similarly, in our case, so this is done in our lab, and we see that we were able to form a networking kind of structure by using the porous setup, and you can see this is the raw silicon wafer. This is the raw silicon wafer, which is having a very high reflectance in the range of visible. And you can see after etching 10 minutes, 20 minutes, and 30 minutes, you can be able to see that you can minimize the reflectance incoming photon. You can keep the light as much as possible, and you see this less than almost in this region 5%. So that is, we are very much happy about that, and we could even make devices based on this kind of structure. And the other trial was made to make with the metal assisted chemical etching, and what we did was we were spreaded with a different concentration of silver nitrate, and we could see that the surface of the silicon wafer has a different kind of morphology, and we thought of checking how much the penetration of this porous has occurred. And we have shown here it is several microns, and this was published, and you can see the reflectance is really minimized in a quite differently than that of the electrochemical etching. And here is another example stating of silicon crossing nanowires with pores. And here as well, you can see that we were able to make two different structures. One is the porous as well as the nanowires inbuilt in this structure. And we again look at the TRS reflectance spectroscopy, and you can see that we are even almost close to the reflectance. The reflectance is almost to zero with this kind. So you see that this will be very interesting type of nanostructure on the device that we are going to do. And with the silicon hybrid nanostructures, we are also able to, this is all made from the metal assisted chemical etching, and this is kind of, you need to give a trial for with many different etching silver, or you can take silver, copper, or other noble metals that can be used for etching. And this is another interesting high aspect ratio of silicon nanowires, where you can see their wires is almost more than 13 micrometers in this length. So this is the first report that we were able to achieve such a high aspect ratio of silicon nanowires, and you can see this is the red one. In 15 minutes itself, we were able to reduce the reflectance quite high. And the last one is we were able to make an inverted quadratic structures where this inverted quadratic structure would yield a black color surface, and this can be used effectively for making photovoltaic devices. This was done in a recent days, and we are working on this to get a device based upon the inverted quadratics. And this is the device performance from our lab, and we see that we were able to obtain like 18.45 amps per centimeter, the local circuit is really huge compared to the people that have been already reported in the literature. So this is the first device that we have made in our lab with the not sophisticated equipment that we have seen in the video. This is promising for us, and we will be trying to do further more optimization, and we will be able to achieve the current scenarios, efficiency of silicon-based solar. Okay, so this is what the first generation for. If you have any questions on this one.
Router 10 minutes or 20 minutes after it. This board is silicon we have it. Whether it is used in auto electronics and optical applications.
You can use them in the auto electronics purpose.
Since you are about the negligible height tag protection, but it is after.
Yes. So silicon, you know, silicon is used in all the devices. So for computers, it is silicon, microchips, transistors, all are based upon silicon. That is why the concentration is still holds, and we are easily adapted. Technology is easily adapted, so that we can utilize already existing devices. Any questions on the first generation? Questions from the audience? Okay, we will have a question. I think I will sign it first, but you are both welcome to actually your area of studies. And okay, I think the time is up. I am not going to leave you. I will mention 5 more minutes. Questions? I was talking about the time is first and third generation. I just quickly say what this third generation solar cell is of. So this is mostly nice generation solar cells. If you look at the leaves, you know photosynthesis. So just copy the and imitate the photosynthesis. So that is where the license phase solar cells. So you have an substrate which is a conductive glass, and a semiconductor which is a very high or large band gap, and you have a dye which is like either you can use metal dyes or organic dyes, and then you have electrolytes and you have a counter. So this is how the cell arrangement is. This is how, but this type of cell are mainly recommended for indoor applications rather than outside the world, because this is not yet commercialized, because it really have the issues of stabilization. So the dye will not be stable with very high illumination of sun, and it will degrade quite slowly. So that is the main issue. And the mechanism is, you can go through it, but the assembly, which I would like to say is very quickly, I can show you the assembly. It's much easier and simpler compared to the silicon first generation. So what we take is we just take glass plates, cut it into small pieces that what we are in the desired manner, and then we will try to use the pastes which are made from titanium dioxide or zinc oxide, and then we coat it on the conductive glass, and then we will fire down transform PVC to make it adhesive, and then you make a dye solution, and you dip the plates into it, and left it for 24 hours, depending on the process that you are going to use. You can leave it with the hot process as well or cold process, and then you can make the assembly by using a counter electrode made from carbon or platinum, and then you will do assembly of the cell, and this is the device, and you see this, you can have an output voltage, and you will have a small fan also. So this is very simple, and people are currently and widely trying to make research publications on this. And we are also working on this, and especially on the side of glass plates. So I was telling about the conductive glass. So we have made different type of conductive glass and try to make the solar cells and try to study their properties. We are mostly focusing on only the photoanode as well as the conductive plate. And you can, each of the layer research activity is very enormous, but we are only focusing on the conductive plate as well as the photoanodes. As you see here in the photoanodes, we were trying to make different type of morphologies and different types of rods and other aspects of we can reverse light, and we have this type of structures, and we can compare with how much different efficiencies we can able to get it. And this is quite good, but it is very problematic if you could measure it on the next day, you will not get the same with this type of process. So that is very challenging, and people are trying to move on to the next type of material, which is based upon perovskite materials, and this is still an open challenge. And, people are trying to optimize the conditions to achieve a stable electrolyte and a stable diet that could lead a very high efficient devices. Okay, thank you very much for your kind attention. Any questions, or I can take it up? Yes, sir. If you want to read a bit more on the solar cell, I would really suggest you to look at the PTCD book. That's it. You just read it. Google the PTCD book. Google. I think that you can get many fine videos and education sites where the Australian people were trying to make a site that everyone would take for free of cost.
So, as an experimental material scientist, what will be your advice to the theoretical physicists for trying to model solar cells? What should they do and what should they don't do?
I'm totally go with your hand because I won't advise, but it would be nice to we people are mostly looking at the theoretical people's study and try to achieve, because you have a different thinking as a theoretician. You will be using very different materials that we cannot handle. For example, we know that zinc antimony arsenic is a very good thermal material that was given by a scientific theoretical person. But making and handling arsenic is very difficult. So that's a very big challenge. But your question is what I can advise for a theoretician, of what kind of problem that we could look at. Is that correct? So which generation you are talking about? Third generation. Third generation, I think solid state electrolytes, because dye is a very big problem and it's very expensive. 1 gram of dye is ruthenium based dye is more than 36,000 rupees. And it would, so if you could find a way to give as much effective as ruthenium and suggest some kind of material that could be used for replacing the dye as well as the electrolytes. If someone would give a technical approach to that, that would be great.
Thank you.
Thank you so much.
Sir, general question, sir. Sir, normal நம்ம environment affect பண்ணதுதான் நம்ம சோலார் சிஸ்டத்துக்கு சோலார் பேனல் மூலம். இப்ப உலகம் முழுக்க நம்ம சோலார் பேனல் ஸ்விட்ச் ஆகும். சோலார் பேனல் ஸ்விட்ச் ஆகும்.
solar cells.
No, sir, solar panels use பண்ற மாதிரி செட் பண்ணலாம் சார்.
ஃபுல்லாவே கவர் பண்ற மாதிரி.
No sir. இப்ப நம்ம எல்லாத்தையும் கோல் யூஸ் பண்ணி கரண்ட் எடுத்துக்கலாம் சார். அந்த மாதிரி சோலார் பேனலுக்கு என்டர் வேர்ல்ட் ஸ்விட்ச் பண்ணலாம்.
ஸோ இப்போ நம்ம வந்து சன்லைட் மீட்டர் பக்கத்துல இருக்கிற நமக்கு வந்து சோலார் பேனல். பட் இதுல ஃபோர்ஸ் இருக்கிறவங்களுக்குலாம் வந்து டிஃபிகல்ட் டு கெட் சன்லைட். So, for example, you take Norway, because Norway is the main people who are working on solar energy production, but they do not have sunlight for 6 months. So, but they are sufficient with water, hydro water. So, under the energies, energy, solar, water, wind, tidal energy, geothermal. So, depending on the earth availability, you can go for it. But if you go for solar energy, that is also well and good. But there is another issue which has been not addressed well. If you stop the sunlight falling onto the air, that is another drawback, in my opinion. And there is some adverse effect may also have.
Sir, அதோட லைஃப் டைமே குறிப்பிட்ட நாள் தானே சார்? சோலார் பேனல்.
No, it's first energy process it can go up to 25 years.
Yes, sir. After 25 years, there will be mass disposal, sir.
No, it is not like you don't throw it. You don't need to throw it. Lifetime current scenario is 25 years. But if it continues to work, you can keep it. Yes. It's not like going to die. It's not going to die. If you can manage very well and keep them alive, it can be there for almost more than 20 years.
Thank you.
This is a basic question, sir. I wish to know how we actually maintain the solar cell, because we have to keep the solar cell to get more sunlight. So they use fresh water for it. Is there any other method for maintaining the solar cell? Because fresh water is I totally agree with you, because you can put it in another perspective. It's solar panels. So to maintain the solar panels, people have been using fresh water for cleaning the. So people are working on finding hydrophobic dust-free glasses. So if we are able to get a dust-free glass, I think we don't need to use water. Right. Because not only that, I just want to also, because you put a next question, I just want to add up, especially in our Tamil Nadu region, we also have this honey farm near my village. So I visited there, and there is a big challenge that the state of the birds. That state is really a drawback of getting the efficient of that particular device. So how to clean it? So this is a big challenge, and people are working on to find a hydrophobic type of material. I think if you are from that village, I think they have also a problem of finding that they are using the groundwater for cleaning the panels. So that is really addressed, and it has been people are working on developing such type of layers to avoid and create a dust-free layers. Thank you. Thank you.
Sir, I have a question, sir. Sir, you talked about the reliability of dye-sensitized solar cells. Since it is not reliable, we are going for perovskite structures.
What I mean is, it's not, it has some issues. So, to tackle the issue, perovskite may be one of the pathway that we can address. So, But what is your question?
Still, perovskite solar cells are not having good stability. After 1 week, they are decomposing.
So if you are talking about iodine-based perovskite, yes, I agree. But if it is other than iodine-based beryllium, I think we can hold it for a longer.
Thank you, sir. Thank you.
சார் சார் ஸோ மெத்து கேள்விப்பட்டிருக்கேன் சார் என்னன்னா இப்போ எர்த்தில் இருக்கிற எல்லாருமே வந்து சோலார் செல்ஸ் வந்து யூஸ் பண்றாங்கன்னா எர்த்தோட டெம்பரேச்சர் இன்க்ரீஸ் ஆக வாய்ப்பு இருக்குமா அப்படின்னு ஒரு மெத்து நான் கேள்விப்பட்டிருக்கேன் சார். இஸ் இட் ட்ரூ? இஸ் இட் பாசிபிள்?
Yeah, that's what that guy was asking. That is really a big issue. Because if you try to cover all the, for example, cover the sunlight everywhere there, there will be some change, ecological change. But we do not know how that would be. And it's still over.
Thank you.
Any other question? Thank you, sir.
Thank you so much for informative talk.
We have some wafers for if you would like to see both wafers and solar cell device. That would be really interesting. He can pause on. I think he is your alumni and he is trying with me as PhD research scholar and he will be involved in one of the projects that we have. Mr. Alvin.
Thank you, sir, for your technical lecture. It was simple and quite explanatory. Thank you, sir.
Welcoming is like connecting the others to perform it. To start our program, I cordially invite Dr. S. Anandar, Assistant Professor, Department of Physics, to welcome the gathering.
கண்டிப்பா கண்டிப்பா.
respected Reverend Father Anandar, Vice Principal, respected Dr. A. Sundarraj, Deputy Principal, respected Head of the Department, Dr. K. S. Joseph Bishop, respected Dean, Dr. A. Sanmuraju, respected Organizing Secretary, Dr. C. S. A. Raj, respected Dr. Inigo Valan, and my dear students, good evening. I am very much privileged to welcome you all for the valedictory function of two-day International Conference on Recent Trends in Material Science 2023. I welcome Reverend Father Anandar yesterday, Coordinator, Jesuit Higher Education Commission. He is a very simple and a highly confident person. He always encourages us to conduct many programs for the betterment of student community. We are very happy to have you here, Father, to grace this occasion. Welcome you, Father. I am equally privileged to welcome our respected Chief Guest, Dr. A. Sundarraj, the Deputy Principal. He is the backbone for all the academic activities of our college. You are highly motivated and inspiring, and I am very sure that you will enlighten our students with the precious words. Welcome you, sir. I extend my warm welcome to Dr. K. S. Joseph Wilson, Head of the Department. He guides us and enlightens us with his vast experience. I welcome you, sir. Also, I welcome Dr. E. Sanmuraju. He is always support us. Welcome you, sir. I welcome Dr. C. S. A. Raj, Organizing Secretary of RTMS, for successfully conducting this conference through his meticulous planning. Welcome you, sir. I extend my welcome to Dr. I. Inigo Valan for his support to conduct the paper presentation in successful manner. Welcome you, sir. Next, I would like to welcome my dear faculty members. Without your hard work and support, and even like this is not possible. Welcome you all, my dear faculty members. I would like to welcome all the participants, research scholars, and my dear students. Welcome you all. Thank you.
Thank you, sir, for your warm welcoming. This smiling face is a source of energy to all our students. I feel privileged to invite Dr. Reverend Father Anandar Estate Coordinator, Jesuit Higher Secondary Education Commission, Madurai Province, to address the gathering and distribute the prize.
My dear Deputy Principal, Dr. Sundarraj, HOD, Dr. Wilson, and other professors of Physics Department, and my dear students from other colleges and students from our own college. Very good evening to all of you. I do not know in what way I will be connecting physics because I am from arts faculty and a literature man. But for the principal, though he is also a literature man, he was taking a class on material science. It seems. So I will talk of my own experience in physics. We study metaphysics. There is a subject called metaphysics. Beyond physics. In beyond physics, we study there is essay, that is, so this is a mic, and the function of the mic and everything is called essay. And the essence is there. For human being, what is the essence? That is, we study soul. Soul is our essence. The potentiality. And many times we cannot, we say, all the scientists, we say, there is no soul for any material, isn't it? It is theologically also applied and it is correct. But many times, we Indians and Tamils, we have our own celebrations with our own materials. And we worship also. Once I was going by bike. When I started the bike, there was very little petrol in the bike. And I was talking to the engine, my dear engine, that is my bike. I have been relating with that bike. I have been owning, and every day, whenever I take, at least I wipe and also I kiss the bike every time when I take. So I have made a bond between my bike and myself. There is a bond between us. And once, many times, there will be very little petrol. With very little petrol, I will have to go travel all the way, at least to Chekanurani, to fill the petrol, and then I have to go further. So till Chekanurani, I will be talking to the engine. What will I talk? My dear, sweetheart, don't put me down. I am totally believing in you and please help me. And fortunately or unfortunately, it always helps me because it is my sweetheart. So this is the bond between we, all the people, not only Tamils, all over the world, we develop our own bonding towards some materials. Okay, so this is a new material science that I am thinking of and I was experiencing. I do not know whether it will be anyway relevant to your subject and your seminar, but this is my experience. As a literature student, I can talk to my own bike, or I can talk to my own pen, I can talk to my own computer, and I can order it, and as I like, I can make that thing to work. So this is in this way, I do believe that this material, all the materials, has got some potency beyond that material. So that is my scientific calculation, but it is never proved. I cannot also prove, and I don't think that anybody will take courage to prove that there is something beyond this material. But this is what I have experienced. But anyhow, you are all well educated and you are all attending this seminar or today. I really congratulate and appreciate our physics department for organizing this wonderful seminar, and it is useful and it will be useful for you all. And I wish all the students to be researchers so that you will be in future helpful to the nation at large. So I congratulate all the students who are from outside and also our students and the department for taking this. Thank you very much.
Thank you very much, our beloved brother, for your thought-provoking words. In the physics lab, we follow strict silence because silence helps us to concentrate. The same way, this reflective silent walk shows his sincere commitment to the growth of our students and college. I am so grateful to invite Dr. A. Sundarraj, the Deputy Principal of Anandar College, to share his views and empower us with his reflective words.
Reverend Father Barasu, Principal, respected Dr. Wilson, PG and Research Department of Physics, and convener of this two-day International Conference on Physics and Materials Science.
Dr. Sandor Raju, Dean for Academic Affairs, Dr. Valamanu's IPAC Coordinator, Dr. C.S. Raj, Organizing Secretary of the 2-day National Conference, Dr. Irigo, outstation participants from other colleges and universities, faculty members of the PG and Research Department of Physics, and my dear students, good evening to all of you. I am very much pleased to associate myself with the PG and Research Department of Physics and to deliver valedictory address on this occasion. I take this opportunity to appreciate Dr. Wilson and the organizing committee for organizing this 2-day international conference on Physics and Trends in Material Science in collaboration with Loyola Institute of Practical Energy Life, Chennai, and inviting eminent resource persons from different institutions from different parts of the world. Yesterday and today, we have deliberated 7 topics, and around 100 members were presented in the 2-day program. We sincerely thank all consultation participants and paper presenters for attending this conference and making this conference a grand success. The Department of Physics is known for conducting research. Their contribution to the field of science is amazing. I wish them to continue their contribution and continue the good work. Coming to the international conference, originally the aim of this conference or any conference or workshop, seminar we organize, the aim is to bring together leading academicians, scientists, researchers to give a platform to exchange their experiences, research results in their fields. Particularly for this conference on material science, I think the purpose is achieved. In addition to what we have discussed yesterday and today, I would like to present a few aspects related to the topic in brief. The transformations occurring in the energy, automotive, logistics, manufacturing and construction industries in combination with evolving industry 4.0 innovations. You may be aware that we are moving towards industry 5.0 innovations now. So there is a demand for new materials. The materials industry trends range from solutions for sustainability, lightweighting, 3D printing, and surface engineering, as well as the development of intelligent materials, nanoformulations, and advanced composites with enhanced characteristics. Moreover, the widespread application of artificial intelligence and machine learning data management practices stimulate scientists to explore and develop novel materials. As per innovation map outlines the top 10 materials industry trends they have identified for 2023. There are 10 top 10 materials. The first one is sustainable materials. The immense volume of waste generated during the use and production of materials is a challenge. And as a result, it forces to develop new recycling technologies and to formulate new regulations. Practically, all industries face challenges while rearranging their internal processes from the perspective of materials life cycle. Companies in the construction, automotive, packaging and manufacturing sector are integrating sustainable materials to lower their carbon footprint. Increase in carbon production leads to global warming and other consequences. Coming to the second, responsive and smart materials. Advancement in materials science enables smart materials with programmable properties that perform or respond
to stimuli from external factors. Then the third one, according to top 10 trends, is nanotechnology. Advancements in nanotechnology show that the characteristics of materials at a nano scale differ from those of their bulk equivalents. The preparation of nanofibers, nanotubes, electrodes, quantum dots, and other materials enable an almost infinite source of value addition. This includes a strengthened performance of industrial products retailed at an atomic level. By leveraging the nanomaterials, modern companies secure their competitive edge, specifically in electronics, energy, mobility, and manufacturing sectors. Coming to the fourth trend, that is additive manufacturing. Emerging additive manufacturing facilities try to evolve beyond traditional thermoplastics and apply materials that offer greater flexibility, customization, and functionality by producing lesser waste. The progress of 3D printing technologies in turn upgrades in metals, alloys, ceramics, fibers, and their components. It also encourages the appearance of completely new and durable polymer filaments with improved conductors, melting, and chemical resistance, among other problems. The fifth trend is lightweighting. We know there is a need to reduce weight of the devices we use, and we look for less weight devices in the case of mobile phones to laptops. Various industries from aerospace to mobility, the search for innovative ways to reduce excess weight and consequently provide superior fuel efficiency and handling. This demands research into materials like aluminium, magnesium, and titanium, as well as strong plastics and carbon fiber. These materials offer industries the option to reduce their environmental and operational burdens. Moreover, lightweighting innovations in the materials industry also provide safety and reliability levels on par with weightier equivalents. The sixth trend is material informatics. Big companies today employ a data-driven approach for materials, enhanced by principles of informatics and computational techniques, as well as machine learning and artificial intelligence. This allows them to arrange and model materials data in a meticulous manner. In addition to optimizing the ability to reliably deriving scientific insights from complex materials data for research and development, for time saving and labor conservation. Then the seventh trend is advanced composting. The rapid increase in the number of industrial applications also results in the development of a variety of composite or hybrid materials. In pursuit of improving performance and regulatory compliance, as well as reducing costs, emerging startups innovate within resins, fibers, substrates, matrices, and features to build custom composites. These composite solutions provide advanced user-specific applications, primarily for the infrastructure, energy, industry 4.0, and mobility markets. The eighth trend is graphene and 2D materials. Regarding graphene and 2D materials, breakthroughs in nanotechnology allow materials science companies to configure pathways for 2D or single layer materials. Possessing inherent thermal conductivity and mechanical strength, and 2D materials endow industrial applications with enhanced capabilities. However, a majority of 2D materials are still under development, excluding graphene, like styrene and phosphorine. The most promising jewel in the field of 2D material is graphene. Graphene will transform our future. As the first 2D material successfully commercialized, graphene improves tensile strength, intra-sheet strength, surface durability, electron mobility, flexibility, and thermal resistance. These sectors which are utilizing graphene input are the sectors which utilize graphene are electronic displays, supercapacitors, automotive, construction, paints, and plastic manufacturing. Then the ninth trend is surface engineering. Exposed to continuous wear and tear, corrosion, UV rays, and other harmful effects factors, industrial surfaces require coatings that demonstrate improved durability. This is essential for protecting automotive, industrial, agricultural, marine, and manufacturing assets, as well as for increasing productivity. Besides, engineering innovations offer the possibility to crack surfaces, properties of hydrophobicity and homophobicity, self-cleaning and smoothing. Following the COVID-19 outbreak, surface engineers work to undertake efforts to master antimicrobials for more reliable protection in both industrial and non-industrial sites. And the last trend is materials management 4.0. Industry 4.0 is introducing the implementation of its practices in materials management, handling, and processing, spanning autonomous mining, advanced automated fabrication to robotic manipulations and cloud computing. The material sector is being rapidly digitalized and interconnected. As a result, the development of new materials comes in parallel with their industrial adaptation through the fourth generation of industrial technologies. With this information on recent trends in materials science, I conclude my valedictory address. Once again, I appreciate Dr. Wilson and the department for organizing this two-day international conference, and all the participants for your contribution to this conference. Thank you. Wish you all the best. Salam alaikum.
Thank you, sir, for your inspirational words. I request Professor Bhaveshwari to distribute the certificates.
Good evening, everybody. This is the moment of distributing certificates. May I request Dr. Anandar to kindly give away the certificates. Mr. John C. from Kalasangam Academy of Research and Education. Dr. Revati, Kalasangam Academy of Research and Education. Fadila Gandhi from Fatima College, Madurai. If the participant is not coming, one of you please come and collect this from that institution. Diana from Kalasalingam Academy of Research and Education. Aishwarya from Madura College. Dhananjay, Madura College. Manishwari, Madura College. Mohammed from Madura College. Sabuka from Madura College. Arul Here from Karnataka University. Ramya Priya from JK College for Women. Priya Lakshmi from Jeda Janapakam College. Arul Priya from Jeda Janapakam College. From Jeda Janapakam College. Megaraj Begum. Sharmili. Kavita from CPA College. Arul from Arul College. Eachwari from Jeda Janapakam College. Manikandan from Colorado Campus College. Shakti from Colorado Campus. Swati Santaram from Kalakatta Academy of Research and Education. Jhansi. Maria Chiva from Anandar College. Elena Nancy from Lepito College. From Anandar College. From Kyama College. Sri Ravindra from Anandar College. Anandar College. Kalyani from Agricultural University. Main father of International Science. Anandar College. I request the research scholars and faculty from other institutions to come and collect your attendance certificate. Jhansi. Queries. Fuel and currents are essential factors for the system. In the same way, tanking makes the heart churn, which makes our life beautiful. I feel immense pleasure to welcome Dr. I. Ingovaran to thank the gathering. So please.
such a prayer that cannot be seen or touched, must be felt by heart. Respected dignitaries on the dais, faculty members and student friends, I feel privileged to propose the vote of thanks on behalf of the organizing committee for this two-day international conference on recent trends in material science. First, I thank the partners of our college, Reverend Dr. John Prakash SJ, Director, Reverend Dr. Gilbert Camillus SJ, the Secretary, and Reverend Dr. Gordon Rufus SJ, the Principal, for inaugurating and blessing the conference. I am glad to thank Professor J. Kumar, Vice Chancellor, Madurai Kamaraj University, and Dr. Surati Kuhu, Head, Department of Chemical Engineering, Chulalongkorn University, for their keynote address and pinpointing some of the recent research topics in the field of material science. I am much honored to thank the guest of honors of today's valedictory function, Reverend Dr. M. Anbarasu SJ, Coordinator, Jesuit Higher Education Commission, Madurai Province, for introducing and enlightening us about metaphysics. His presence as the Higher Education Commission Coordinator adds value to the conference. Thank you, Father. Extend my sincere thanks to today's Chief Guest, Dr. K. Sundarraj, Deputy Principal, Anandar College, for his informative address on validating the key points of importance about the conference to the gathering. Thank you, sir. I thank Reverend Dr. Francis Xavier J. Rector, Loyola College, a distinguished scientist, for sharing his knowledge on the recent advancements in the energy storage devices. I also thank Dr. M. Silver Ayagam, Director, Loyola Institute of Frontier Energy, Loyola College, for their support. On behalf of the organizing committee, I express my sincere gratitude to all the resource persons who have shared their knowledge through their scientific lectures and explaining some of the complex research topics in simple words. I honestly believe their lectures will encourage the young minds to march forward into research. I express my sincere thanks to the convener of the conference, Dr. K.S. Joseph Wilson, Head Department of Physics, Anandar College, and Dr. J. Merlin Shaina, former Director and member of Loyola College, for arranging the whole event. Thank you, sir. I extend my thanks to Dr. A. Shanmugaraju, Dean Academics, and Dr. S. Balanars, IPSC Coordinator of Anandar College, for their support in various. Thank you, sir. Thank the organizing secretary, Dr. C.S.A. Raj, Assistant Professor at Anandar College, for his keen focus on organizing this conference. Thank you, sir. I express my sincere thanks to the teaching faculty members for their tireless efforts and constant progress in every activity of this conference. Thank you, my dear friends. I extend my thanks to the non-teaching faculty members and caretakers for their help and support. Thank you. Finally, I thank all the participants, research scholars, and student friends for making this conference a successful. Thank you.
Thank you for the fullest cooperation from all the corners across the globe. So we will see next year RTMS 2024. Thank you. Bye.
Small announcement to all participants.